make the videos.
All right. People in the room, I think, should be able to hear me. Could people online hear?
Yes.
Awesome. I'm going to give people just like another minute or two to join before we get started here.
So Bill, when people have questions and discussion, will the microphones pick up?
It looks like it's picking you up right now. Yes.
I guess we'll get started. Welcome to the CESM Software Engineering Working Group meeting, which we haven't had a winter meeting in a while, so it's exciting to have one this year. Largely thanks to Brian for all of his organizing of this meeting and pulling this together. For those who don't know me, I'm Bill Sachs. I am the NCAR co-chair of the Software Engineering Working Group. And we also have Lisa, who has also helped organize this meeting. Do you want to say hi, Lisa?
Hi, everybody. It's a pleasure to be here and participate in this NCAR meeting.
And yeah, Lisa's at NOAA, and so we've enjoyed these last few years having her help with kind of keeping the NCAR NOAA collaboration alive and well and active, partly through her great involvement in the software engineering working group here. So just a few logistical things before we get started. First off, we are going to have a optional, but hopefully you can all make it, post-meeting gathering for those who are here in person after the meeting around 4:15 under the sun. And so that's just down the hill in the Table Mesa Shopping Center. So yeah, hope you can join us there. And then just want to remind everyone of the code of conduct. So as you're presenting or asking questions or participating in discussion today, just remember these points to please try to offer constructive feedback, share the air, so give everyone a chance to speak, acknowledge teamwork, encourage innovation, show appreciation for everyone, the speakers and others around you, and consider new ideas. We have a great agenda set up this morning that I'm really looking forward to. And so we'll have a set of talks, followed by a break this morning, more talks and lunch, and then we'll get into some more exciting things this afternoon. Anything else? We will be, for those who are remote, we will be following the chat. You can use the chat or raise your hand for if you have questions. And this is being recorded, so just keep that in mind. All right, I think with that we can turn it over and get set up for the first talk, which is from Dom Heimzeller on expanding the UFS to multiple dynamical cores. Yeah, we will. For those who are here in person, we will present from here if this works. So let's see. We can get this going.
I think that works because those Google Slides don't have PowerPoint.
Oh, did it get converted to PowerPoint? Okay, you might have the okay. I think we have a few extra minutes here. What is this? Do you have the you have the Google? Okay, well let me. Yeah, if you want to, if you have the original Google Slides, I wonder what. Well, this is in the PowerPoint. I don't know why it got converted to PowerPoint.
Fine.
Okay.
See what happens.
Okay. Oh yeah. Thanks. Okay. Focus all the way up.
Great, thanks.
All right, and speakers will try for 15 minutes, and then about 5 minutes of question and transition. And so we'll give you a warning with about 2 minutes left, so like the 13-minute mark. Right?
All right. Good morning, everyone. So my name is Tom Heinzel. I'm from the Joint Center for Satellite Data Assimilation. My wife and I are here talking about the UFS and Campus NICOR. That I'm also co-chair of the software architecture and infrastructure cross-cutting team at NOAA, together with Leisure. And so this today is about the opportunities and challenges of expanding the unified forecast system to multiple dynamical cores. Can you hear me well? Yeah, okay, great. So just to remind everyone here, one of the purposes of the unified forecast system is to simplify the operation of forecast suite of NOAA, which used to be 21 independent standalone systems, code, applications deployed into operations. And this was supposed to be cut down into 8 UFS applications that all draw from the same source code and that have the community involved in the development of the code. Now, that's one of the main reasons of the unified forecast system. So this effort started almost 7 years ago by now, and there are quite a few success stories, and one of them is the UFS Global, so also better known as GFS, and another success story is the Hurricanes HASH application. There are some issues, however, with the regional convection allowing model, that's the Rapid Refresh Forecast System, RRFS, for the details of the convector structure and excessive precipitation biases. And in short, that model in this first version doesn't meet the operational requirements. And of course, people spend a lot of time trying to mitigate this in the existing code base, and that turned out to be not successful. So NOAA leadership went out and requested 2 studies. One of them was turned into a white paper that describes the problem of the RFS and which mitigation strategies they have tried and what else we can do. And then also, as a follow-up, more or less a study to estimate the effort of adding another dynamical core to the UFS. So first question is, of course, why is it the die-core? Why do we think that's going to solve the problem? So quick reminder of what the RFS looks like, if you haven't seen this. So it uses the FE3 dynamical core in the limited area model configuration. So the updated and has a 3-kilometer grid spacing over a huge domain. That's this red domain that you can see there in the bottom right, that encompasses all these different domains of the applications that the RFS is supposed to be the successor for. So data assimilation, it includes smoke and dust, and it runs a deterministic forecast at high frequency and then also deterministic and ensemble for longer. So after much work, Jacob Kali and the team writing this white paper determined that the culprit is the CD grid structure of the model. So that structure in FE3 that represents rotational modes better than just the C grid, which sounds good at first, but it also requires enhanced damping to remove the excess energy pattern near the grid scale. And so they found that the combination of the grid choice and the necessary damping leads to wide and stronger updrafts, stronger storms, and more precipitation. So here on the right is just one example that shows the GPF kernel density estimate, where the red one is the RFS, and then the blue and the WRF and CM1, 2 established cores that look quite different. So can this issue be fixed in FE3 or not? That was the first question that they tried to ask. And so I'm quoting from the paper here. It's important to realize that the changes needed for the FE3 dynamical core are significant enough that the resulting code would effectively create a second dynamical core within the EFS. One that first has to be written, not from scratch, but from some other code. So obviously another alternative is to, instead of writing something new, take an established die core and put it into a unified forecast system as a second option. And the choice here that was brought up was MPES, because it has established limited area model capability. MPES JEDI has demonstrated DA capabilities, and JEDI is set as the DA system for the RFS, regardless of what the die core is. And MPES has also demonstrated promising performance for convective applications using physics that are pretty similar to what's run in the RFS. So one then goes and has to ask, okay, which of these 2 options is cheaper, which gets us there faster? What is more future-looking, more promising? So if you want to read the full glory, here's a link to the slides, the white paper from Jacob Kali, and it's a really good paper, so I encourage you to look at that. So the second part then, of course, is a Tiger team that was created to scope out the effort of adding Ampers to the UFS in order to answer that question: what is cheaper, what is more feasible? So the usual suspects, you may know this from the software architecture and infrastructure cross-cutting team are Dan Rosen, myself, Dustin, Jun Wang, Kevin Weiner, and Lisa Bernadette. And the scope of our work was to research the technical work needed to bring a new DICOR into the UFS. So be generic in terms of the application of the UFS, but also focus on the RFS. Be generic in terms of which DICOR, but also look at Ampers specifically. So we went out, we collected feedback from UFS application leads, from MCube, and from CGD, various people, and we compiled all this into a report. Jun Wang et al. Here. It's a PDF that you can have a look at. So before we go into the details there, let me briefly talk about how to integrate the Ampers in the UFS, or what part of it. Because when you talk about Ampers, there are different meanings of it. So when people talk about Ampers, what gets released to the public, they usually refer to the Ampers standalone, a forecast model, which is the atmospheric model Ampers A, the DICOR with physics, additional codes, a driver, and infrastructure that is shared with other Ampers components. The other components, however, like Ocean, CESM, are not part of the public release. If someone talks about Ampers in CSM or CAM, or CMAP Ampers, then that usually refers to the DICOR, the Ampers DICOR, that is integrated in the CESM CAM, and it draws the DICOR code directly from the Ampers standalone repository. And so for the UFS, this was deemed to be the approach to take as well. Similar to CAM CMA, we'll pull in the Ampers DICOR code and use it within the existing UFS application instead of creating another application. That would defeat the purpose of the UFS, where everything draws from one code base. So having a single modeling system has many advantages for NOAA and the community, so this is the way to go. All right, we're going to walk through these different pieces that we have sort of singled out and looked at separately. We're going to go through those relatively quickly, and we can come back and discuss that later in questions or following talk. So let's start with the UFS atmospheric component. This component is currently called FPV-ATM. It's the coupling interface between the dynamics, the physics, the atmospheric I/O, and some external components. And so this needs to be abstracted and generalized, and we'll change the name to UFS ATM to facilitate the introduction of a new DICOR, such as Ampers. And of course, there's a lot of opportunity to clean up and restructure while you're at it. In terms of code management, Ampers is going to be a submodule of the UFS ATM, and the code will point direct to the official repository at MCube. The interface will stay under the UFS ATM repository. So this is pretty similar to how Ampers is used in CSM, as I said before, but it's also very similar to how FE3 is used in the UFS. So there's not that much change in terms of how we do things. That, of course, requires good relationships between the UFS and the Ampers teams, because there may be code changes that need to go back into the Ampers repository to accommodate UFS needs. And maybe also dollars, because code management doesn't come for free typically. So if we then go through a typical modeling process, we start with the pre-processing. So there are existing tools to interscript to data and drive Ampers. That's great, that will get us started, but we will have to do some work if we want to ingest the GFS v16 analysis data that's available as netcdf files on the native CubeSphere grid. You know, that's got all the variables, got all the levels on these kind of things. So there's some work needed here. There are also existing tools to interpolate static data sets to the Ampers grid. These will have to be connected to whatever the UFS uses as utilities in their workflows. And we also found that we need to develop some code to generate an input field for certain CCP physics like gravity wave drag. Those are mesh dependent. Things are looking kind of okay for the DAA. So JEDI is designed to, is written in a way that the algorithms and the ops operators are model agnostic, because the whole point of JEDI is to allow for swapping of model interfaces. So it uses the grids provided by the model interfaces to run the DA on the native grid. So it can do that for FE3, it can do that for Ampers, it can do that for Neptune, whatever else it is. There's a lot of ongoing JEDI Ampers experiments, scientific experiments by MCube and JCSDA at the moment. So that's great. We can piggyback on that. And we can also leverage a lot of the sort of infrastructure and software engineering work on the JEDI UFS integration and the JEDI Ampers work that is happening at the Joint Center together with our in-kinds at Cube and at NOAA. So that's not extra work that needs to be done, because regardless of the DICOR, we would have to do more work anyway to get the DICOR to work with the DA system with JEDI. We talk about physics. It's important to note that I mentioned beforehand that there are some physics in MPAS that are being used in exercise for convection allowing modeling that are similar to the HER physics. However, they are not exactly the same as the RFS physics in the UFS. What's in MPAS is older than what's in the UFS, and it's also not using CCPP versus physics in the UFS are all CCPP-ized. And so that's not going to change. The Unified Forecast System will continue using the CCPP framework and CCPP physics in the UFS ATM. However, that doesn't mean that we have to make large code changes in the DICOR, because the DICOR does not talk to the physics directly. In the Unified Forecast System, that exchange between physics and dynamics happens in the UFS ATM atmospheric component. There's one exception, but that will go away with FE3 anyway. So there's quite a bit of work that still needs to be done regardless, but it's not going to be like major surgery on the MPAS DICOR code. Yeah, I'll leave it at that, and we can talk about that later. So the Unified Forecast System is a coupled modeling system. So there's an ocean, there's an ice, there is an aerosol component. And the way this is all realized in the UFS is that the cap, the UFS ATM, the atmospheric cap, is a Luopsi cap that talks to the other components and to the coupler. And so similar to how it's done with FE3 right now, which sits under the cap, is hidden there, and all the plumbing is done within that cap, it's going to be the same for MPAS. So we're driving the DICOR to the existing cap. We'll have to make the connections between the MPAS DICOR fields and the fields that get exposed to the other components, similar to how it's done for FE3. And the good news is, of course, some of this functionality exists in CESM and CAM, so we can just draw from that and use that hopefully. Okay, talking about input and output. So there are two approaches. The first one will get us started, and that's to use I/O to output the data on the native mesh. Then run a utility called convert MPAS that exists to interpolate to that law. That's fine for initial testing. However, if we want to take this to operations, we need more performance. So the idea here is that we then go and develop an asynchronous I/O component, a write component, that can be used by UFS ATM to output the data on whatever grid you need, and it runs on separate processors to not delay the model. So this ties in with plans to develop a generic write grid component for all UFS applications that is, discussed elsewhere. They want ocean and atmosphere and ice to use the same component to write data, not deal with it on a component by component basis. Talking about post-processing, that's again a first step that will get us started, and then we have to sort of think about two choices. The first one is to run an offline UPP on the MPAS history files after they have been converted to lat long. And obviously the first and fastest solution in order to get this process going, but it's also the slowest in terms of runtime. And then we have two options. Basically, we can change the MPAS code to directly output all the post-processing product. That means we have to integrate UPP. We would have to integrate UPP into MPAS to output on the native mesh and then convert to lat long. And the last one, that's the most work, but it's also probably the best choice for operations, is to run an inline UPP within the write grid component. So the write grid component needs to be developed, and then we need to put all the UPP code in place but then we can run the post-processor and output on whatever grid we want. It's probably the most flexible option and the fastest. All right. This was pretty quick, but we can, talk about this later again. I want to
13 minutes. 13 minutes.
Yeah, okay, great. So we have time. So I wanted to talk about the opportunities and challenges for integrating the MPAS DICOR and the physics on my last slide here. So one of the opportunities, obviously, that we have determined that there's a high chance that we meet the RFS version 2 operational requirements with MPAS cheaper and faster than with FE3. Another obvious opportunity is that when you have two DICORs within a modeling system, you have more flexibility. You can experiment with both and use the one that works better for the application that you're interested in. That's for the UFS side. For the MPAS developers, there's also big opportunity here, I would say, because there is, of course, recognition and impact of all the work that's been done here. If you have a product that's used in no operational suite that feeds into many downstream products that are used to save lives and properties, that's a pretty meaningful thing. And of course, there may also be dollars to help fund MPAS development and code management. So that's all beneficial. What are the challenges? Well, one of the challenges is that you need to have a specific set of people to do this work, because you need to understand MPAS well enough, you need to understand UFS well enough, and you need to work, between those people. So you need a number of expert developers available to do the job, and you need them when you want this project to start, and not having to spend a year or two finding those people. Maintaining 2 die cores requires obviously more resources than maintaining 1 die core, so that's one thing that needs to be considered. And then there's one last point that often tends to be forgotten. Once you have a product in operations, that can, at certain times, impose constraints and priorities on the development. If there's something that is wrong that needs to be fixed for operations, and it's urgent, this will have to go in immediately, and other development will have to, be adjusted. So that's as much as I have. I wanted to have time left for questions and comments, so I open it up to the floor.
Thanks. Questions for Dom?
In case I missed it, what resolution are you guys targeting the MPAS for?
So if it's supposed to replace the RFS, then it's roughly 3 kilometers.
Okay, right.
Yeah, over a pretty massive domain. So it's not insignificant in terms of compute.
Do you intend to then run it on CPUs or GPUs or both?
NOAA so far has no GPU capabilities.
Yeah.
And one of the reasons is that, well, the whole EFS effort was always on CPUs. FE3 was on CPUs. Yes, there have been porting efforts of parts of FE3 to GPUs, but that code never found its way into the unified forecast system.
Thank you.
As a part of UFS Coastal project, we are also trying to develop a new component to process the data on the fly. So I see in your slide that you were mentioning about the inline capability to process the data to speed up the process of creating the products. So I think there are some items that's aligned with the UFS Coastal. So maybe that component, it's not ready yet. We are still experimenting it. So that could be an option. Because when you attach to another component, it just mirrors the export fields automatically, get all the export fields, and then you can do whatever you want after that point. So we are planning to make it more generic to process the data.
That sounds great. Lisa, do you know more about this? I'm an outsider in that sense. So,
No, I mean, I'm not so familiar with the work you're doing, but that's great. So that's why we're
Because
here.
they have some needs to process the data for navigation purpose. They have set of square patch around the coastline. So they want to process the data coming from the ocean model along the way.
So like
create the
post-process the
products.
data.
But it will run along with the simulation. So it will create a product for you.
Yeah.
At the end of the simulation, you will get the data.
sounds great. We should definitely pick that up when we discuss the generalized right grid component at the next SAICCT meeting. Jim?
You also talked about an asynchronous I/O component, and I'll just mention that if that is built into ESMF, I think CESM would be very interested in collaborating on that as well.
We already have a right component. We already have a right component that
I/O,
IO.
asynchronous I/O component. As far as I know, you don't have one.
Well, with the IO is done on a different set of processes from where the model is running.
Okay, so but not the one that's built into ESMF that we've been discussing. I thought I saw in your slides an intention to build an asynchronous
So
I/O.
there is one that's tied to the atmospheric component right now. That's asynchronous I/O. But we want to have, well, there is an idea to
More
generalize it
general.
so that it works with the ocean, with the ice, with the aerosols, with whatever the coastal app needs. Maybe that's the idea.
Okay,
And then maybe also bake this unified post processor into it. So
yeah, thanks for clarifying.
There's a question from online from Dave Bailey. He asks, did I hear you say CD grid? Did you mean Arakawa CD? And what components are on this grid?
I think it's the Arakawa CD. Yeah. So it's the dynamical core. The entire die core runs on this grid. There's a lot more to it. So if you are interested in that, and if you understand what, from the question, I take that this person understands the details a bit more. Go and read the white paper, because there's more than just the grid. There's also the vertical coordinate, which is the Lagrangian coordinate, and that is causing problems. So the paper details in many steps what needs to be done to address this problem. And then even then they conclude that there is no guarantee that it's going to fix it. It's just, the best guess. Very educated best guess.
Okay. I think one question is, I'm curious, like how the MPath die core is being used in CESM. Is it really being used, and what kind of relationship do you have with M-cubed, or do you need one? Or is it being used?
Sorry.
The MPath die core in CESM.
Oh,
is
yeah.
is it pretty active?
Yeah, we do
Okay.
quite a bit with them and work with them on
Okay.
that. Yeah.
And you work with M-cubed
Yes. Yeah.
closely on it.
Yeah. In fact, that's what we're playing with right now, large scale 3.75 kilometer roads.
Okay.
Yeah, sounds great. I think we can learn a lot from all your efforts and outcomes.
In fact, maybe I'll say, if you guys, I know you guys have relationships with them too, but this is something we haven't formalized yet, but we're starting a occasional lunch down at M-Cube with CGD software engineers and M-Cube software engineers. If you guys want to come join, I'll pick a wider party.
Sure.
So, yeah. So,
Yeah, we just are starting a MPath development group.
oh,
with,
right, okay.
Some contact with them. I don't know how much they will, engage at this point,
Sure.
but different parts of NOAA and a little bit of M-cubed.
Great.
All right, next up we have Ann Say, who's gonna present yes, the Earth System Modeling Framework. Yes.
So I barely rehearsed, so.
And I should introduce that for those who don't know, and she is the new ESMF core team manager who joined about 2 months ago. So she's getting all spun up, and yeah, we appreciate her being here.
Thank you. Well, I just want to add, I feel like a PhD student in front of all the professors that know about exactly. This is all I know so far. So yeah, so my name is Anne. I am the new ESMF program manager, and basically a replacement for Rocky, which is a huge shoes to fill. So first of all, thank you for patience. And here today, I'm kind of want to talk about ESMF, and I'm really thrilled to join the team with Bill, Dan, Ufuk, Rob, Bob, and Gerhard. And in this presentation, I kind of put like the comments sort of for people to put in. Many is that ESMF would love to get more feedback from the community. We're an infrastructure software team, and we really want to get a more connection with the users so that we know what capability we need to plan. So the goal of this presentation really is since I'm new to the community, I kind of want to bring back the basics. As a long-term product manager from biotech companies, I always want to get back to what is the user needs, what's the problem that we're trying to solve. So in this presentation, I'm hoping to basically first talk about what is the problem that ESMF is trying to solve, and then what are the capability ESMF that's able to solve the problems, basically. And third, future things that we're thinking, and hopefully we can get more community feedback so that we can make those capability a reality. So first, As we all know, and again, this is me, PhD student talking to a bunch of professors here. Earth system is a very dynamic climate system. Given a chemical engineer background, dynamic, I remember that class is probably the most difficult class I've ever taken in system dynamics. But as we know that in order to decompose this complex system, we need to kind of do models and to be able to simulate, to be able to characterize and predict. And you can see here that if without ESMF or some sort of framework, everybody's just going to kind of put models together, link them together, and then somehow, make an application and be able to predict with a very specific focus, like a hurricane application or like a short range weather model. And I'm just using those terms based on all the meetings that I went to, right? And already from this picture, you can see that there's four issues that I kind of extrapolated from all the meetings I've been to. One is that we don't really have, without some sort of framework, we really need a standardized model coupling to be able to allow the model to play nicely with each other. And because all the data are different from models, we have to figure out how to regrid them. And then lastly, all these models are computational intensive. They're talking about chemistry, physics, everything mixed together, and just thinking about those mathematical equations. Basically, you need to have a way to be able to allow the system to function well and to get the output as fast as possible. And lastly, given that I'm a newcomer, if there's an easy way to kind of put all this model, build this model together and drive them, that'll be a win for any newcomer that coming into this community. Okay. So, given that this is an ESMF talk, I'm going to say the solution is ESMF and UOPC. So ESMF is a high-performance software infrastructure used in a couple of Earth applications. And UOPC is a software layer that's on top of the ESMF that provide technical interoperability of model components so that they can share across a couple systems. I'm going to spend the rest of the talk talking to highlight some of the ESMF and UOPC capabilities that I'll be able to address the problem I just solved earlier. But while I'm still at high level slide, I kind of want to point out a couple examples of large system that uses ESMF. One of them is actually just from the earlier talk from Dom is UFS. Because ESMF is almost like the water heater in your house, right? There's need to be a water heater. You need to have some sort of way to provide that water. But do you know the brand of your water heater? Do you know the capacity of this water heater? Those are things that you have to consider if you ever want to expand your house, if you have to have more family coming into your house. So, that's why I kind of want to get back to say that a lot of systems so far are using ESMF. And then if you're a model builder, application builder, please consider, if you're thinking about all the problems that you're solving from what I just talked about, consider ESMF. So these are some of the systems in the US. So you have UFS, you have the Navy part, you have the NASA, and then you have the CESM. Kind of want to highlight there because according to Bill, most of the people here are from the CESM community. So if you don't know yet, ESMF is actually part of your infrastructure library and is being using a lot of the functionality to enable CSM to work. Okay. All right. So the next topic, so that have hopefully motivate why ESMF could be a solution. We want to get into the specifics of the capability that ESMF can provide. And I want to kind of give credit to all those people before me that make all those slides. So I've been a slide stealer for the rest of the next 14 slides for sure. Okay. So first, the first question was, how do we make a standardized model coupling? So ESMF and UOPC provide a unified model interface to all model across application. Basically, we have this thin layer in the UOPC cap, which I think Dom also alluded to in the UFS the presentation. Basically, it's a non-intrusive small translation layer, usually in a single source code file. One of the philosophy of ESMF is that we don't want to kind of mess with your model. So imagine your model is a black box. We just want to kind of put a nice layer on top of it so that that model can talk to other model that has also been painstakingly developed by other people. So we basically, in order to make that happen, we provide and require a couple fields are identified by standard names so that the model internal names you can still stay the same, but you have this outer wrapper that allows one model talking to the other model. We support 1D, 2D, 3D coupling fields and a variety of structured grids and unstructured mesh. And so all this terminology, later on, I can refer you to one of the team paper, but for now, if you don't mind me keeping high level. That's native memory layout already used by the underlying model. Again, this goes back to the philosophy that EMSF is really just want to kind of put a wrapper around your model that you have been developed for a long time, but really just want to provide a way for you to talk to other models. And lastly, New York's cat lives in model components of repository and shared across different community modeling systems. Therefore, there's one UOPSI cap per model. So if you were to, as a model builder, if you were to kind of make your model UOPSI compliant, then imagine your model can go a lot of places, go into a lot of different applications. So it really just kind of, minimize the amount of interface agreement that you need to have with a model. From the biotech world, that is a huge issue. Every industry, every company wants to do their own thing. And then so when we talk about integrating with all systems, it's very hard. So in this community, it's very tight. So it's kind of nice that ESMF can kind of remove that kind of competition to say, here's what you can do, here's the layer that you can do, so that you can talk with the model nicely without really just getting into a meeting, really talk deep about how do we exchange data. ESMF and UOPSI provides optimized communication between model components. So now we define the standard. We also kind of talk about how the communication path between the model can exist. So these UOPSI connectors are generated automatically by the driver. That means that you don't have to write additional user codes for that. Connectors determine the runtime which coupling fields need to be exchanged, removing hard code field mapping. So any software engineer would know hard code, if we can avoid it, that's best, and this can actually provide that. Connector provide fast parallel communication options. So again, going back to earlier that these models are computation intensive. So if you're able to have a framework that allow parallel processing, that'll be good. Connector negotiate the most optimized connection possible, allowing tight coupling, such as shared memory, to loose coupling, such as grid remapping. All this to say, kind of going right back to the point where if you're a model builder and then you were able to make your model compliant, your UOPSI compliant, then your possibility basically expands, your horizon expands. Because as a model builder, it'll be nice if somebody can use your model, right? So if you're basically compliant, then you can see all the system will be able to use. For example, CSMM. Right now, based on the slide, the ICE model, because it's UOPSI compliant, therefore it can be used both by the CSMM and also the Navy Global Regional. So really, it's kind of be able to allow the reusability of code, and then basically making sure that science can be explored and discovered more quickly, so you don't have to bog down and trying to figure out how do I, integrate with one model to another model. So hopefully, I kind of motivate why the model component coupling is how ESMF solved the coupling issue. Now we talk about regridding. So a lot of these models are very different. Outputs are very different, and basically ESMF provide a high performance regridding, provide a fast and flexible interpolation of gridded data. It's high performance because the interpolation weight matrix is generated in parallel in 3D space and applied in parallel. And we'll get into the detail on how that works by using resource management. It provides a wide range of supported grids. Again, every model is different. Imagine, so it's based on my naive thinking is that ocean grid is going to be much different than sea ice or land, but somehow you have to have the way to be able to kind of put them together, and you have to have reports. Multiple interpolation methods. Basically, you have all those methods that allow that's an option for you to try it out, and therefore you really don't have to redo the math yourself. Just so that you can talk to other people, but you can also basically you just have to leverage the ESMF's available sort of interpolation methods. Options, basically, again, another thing about ESMF philosophy is I want to provide options to the user. So imagine we're going to give you this two kits, and then so you can kind of pick and choose what you want to do based on your needs. There are multiple interfaces as part of the ESMF. So there's Fortran, Python, and file-based. Just want to kind of put a plugin on ESM-Pi. It hasn't been widely used, I think, but basically those regridding sort of capability can be exposed offline using ESM-Pi. Now that hopefully I motivate that we can solve the, sort of handling the data, exchange between among models, we talk about performance. How is ESMF going to help you, your application run fast? Really is trying to leverage this parallel programming model. So I kind of put this here. So hardware is my weakest point. So looking at Brian, so he can help me if I do something wrong here. But in the ESM application, the component is basically, we kind of structure in the VM virtual machine that has several PETs, which is persistent execution threads. So the multiple threads allows multiple programming possibilities. And each PAT basically usually point to an MPI, which is a processing tasks. And I'm not sure about this P-thread thing because I haven't heard about that in any meetings yet. So, but since I have it, I will talk about that. But you know what is interesting is that if you do not have a way to do this kind of resource management, your model is just gonna find whatever resource that they want, and it can be chaotic, and it may not be efficient. So ESMF also allows sort of flexible sort of mapping to resources. So you can see in the picture here, ESMF component 1 is mapped to several pet, and then ESM component 2 is mapped to dev, which is a new capability. I just learned this. I think this is basically allows the accelerator to be able to, such as GPU devices that you can leverage. Okay, you probably feel like there's a lot of holes. Yes, it is. But the main point I want to drive to is that I think ESMF provides the infrastructure to allow you to have parallel processing rather than having a model sequentially processing things as to bog down the whole application output. The parallel computation operations. So these are a couple of highlight points: sparse matrix multiply. So by using math-based, those computation also is very costly. So if you can do it parallelly on the distributed data, it's going to be much faster. We want to redistribute the data without changing the values. For example, same global fields move from X number of pets to whatever other pets. You can also scatter together. For example, if the model first came out with the data that's only from one pet, but it's actually gonna, in order to increase the processing power, maybe we can redistribute them to multiple so they can enable the parallel processing. Halo, this is the one that I'm not sure what that's about. Have not learned about that, so I'm just going to say Halo. And then basically it's moving a physical field from a source model grid to a destination. So unlike other operations require physical coordinates for source and destination. So really just kind of helping the model communicate parallel. Here's that slide that some of the questions that people, at least I would ask, is like, I'm a model builder, you're telling me to put another wrapper, like does not slow things down quite a bit. So one of the older slides, and I'm not sure if this is true right now, but the overhead of putting ESMF in the obviously component interface is quite small. It's about 55 microseconds. This is like from a slide that's 4 or 5 years ago, so I'm not sure if it's increased, but consider all the parallel processing that ESMF can provide. I think this is a small cost to spend. One of the things that kind of highlighted in this one of the presentations is the direct reference sharing. So direct reference sharing is a feature in the OPC where components that share the same grid and becomes new data as a reference. So rather than trying to copy data all the time, you just have to point to reference. So I think just intuitively, that would just kind of speed things up. So because you're able to do resource management, that kind of things is possible because if they're on the same pet, then you can kind of do point by reference. And then basically the graph kind of shows how much time you're saving by doing shared reference rather than just kind of reference rather than kind of copy data. Okay. Lastly, as a newcomer, is there a way to 13? An easy way to drive the models. Yeah, so I think many of you are in Dan's presentation about ESMX. So I'm going to do it very fast. Sorry, Dan, if you're on the call. So basically, we're trying to figure out a way for the application level people to be able to build a component quickly and then run the system. And the ESMX is the framework that allows you to do that. And you can see that it uses YAML as a way to be able to define what the components you want to build in the application, and then you run it in the workflow. Okay. And sort of going back to that sort of resource management, this ESMX also allow you to kind of define what pet and devs, which is, for example, GPUs, and which allows you to kind of enable the parallel processing. All right, so last topic in 2 minutes. Basically, these are most recent releases of ESMF. It's a continuous development. Every 6 months or so, we push out something. And going from 8.4 back in late 2022 to recently in November 2023, we push out version 8.6. Some of the bigger things that push out was ESMX. And then I believe there's a basic ESMFC API that's added. And so I'm going to have people kind of read through that. But otherwise, I want to try, the point about this slide is to show that ESMF is a continuous development, and then we will not be able to do so without your input. So these are some of the future feature consideration that we understood from the users. So there's a lot of question about clock management. So hopefully, if I were able to get the right stakeholder together, we can talk about what are some of the features that's needed in the clock management. Bob is working a lot on the field merging and blending. That's also another big feature that people are asking for. State reconcile is also another big topic where we want to scale with a larger number of cores, and then we need to figure out how we can solve that problem. The efficient coupling, the GPUs, and also regional coupling enhancement, which I have been sitting and be talking about that. The ESMX, we already have the framework now. We just want to kind of establish the testing strategy in that, and also support logical component hierarchies. In UFC, I think people are just talking about asynchronous I/O, so something that we want to consider to generalize it. And then call and processing modernization, a lot of talk in build system. How do we make it build faster so that the scientists and the engineer can kind of develop that more efficiently? Interoperability, there's a lot of things that ESML want to take advantage of. Basically, we want to enhance the ESM Pi because there's a lot of development in Python, machine learning, a lot of talk lately, both in the news and in the scientific world, and JEDI, which somebody was talking about. Like, is there a way for us to be able to kind of have ESM talking to JEDI, and then they can each leverage their capabilities? Again, the point of the talk is that kind of say, hey, we're here, we're in the same building. We would love to get your feedback, and that way, that all those features. Very high level, we will understand what are the use cases that we need to do so that we can actually develop a capability that fits the immediate user need. Also, feel free to let us know what problem you're trying to solve, because even though it's very high level, again, remember that water heater. Like, if you have 20 guests coming in, that 20-gallon water heater is not going to support you. So, just kind of think about, even if you have 20 guests, you want to talk to the salesman at water heater people, you probably have to, think about that. We would like to kind of provide some training session. I'm just going to work with, working out with the team member to figure out when there's the next training that we can do. We want to kind of make ESMF easy to use, and I think that's another sort of feedback that we get. Thank you. All questions are welcome. This is an email, and I'm a cat person, so if you have a cat, I love you. If you have a dog.
I'll just mention quickly that major ESMF releases are available as modules on Duratio, but also beta builds are available using the CESM dev module on Duratio as well. So if you want a beta build, you can check me.
Cool, thank you. James, one of the professors that backed me up always has a thing. Next,
so you talked about ESMX. And is that a future thing, or is that currently in the latest release?
It's currently in the latest release.
Oh, it is. Okay.
Yeah, and we want to enhance. Right now, it doesn't have the strategy, the testing strategy part of it in there.
Oh, okay.
And you are able to kind of, put a build system, build the components, and you can run.
Okay.
And if you're online, I don't know if you want to say a couple words, but he's mainly the person that did a lot of the ESMX training. I can point you to the tutorial that he has given to.
Okay, cool. And was that the first release it was in?
I think there's a prototype in 8.4, but I think 8.6 will be best where the most.
Right. Okay. Yeah. Cool. Thank you.
You mentioned some changes needed for machine learning and interoperability related to that. What do you have in mind?
Yes, I would love, this is where I kind of put it there so I can get some feedback from the community, because, already one group is, approaching us about, they have an ML model that they want to integrate it. So I'm looking forward to that meeting with them. But really, from this community, you guys are the end user. We would love to understand what problem you're trying to solve and what are some things that you want to do. And that way, we can consider what are some of the capability and infrastructure capability that we can provide so we can slowly service to you. But the earlier you tell us, the faster, the more likely that you are able to have it when you really need it. So, yeah.
All right. Okay. Well, thank you.
Thank you.
We need to move on.
All right, we're going to continue with this, the theme of infrastructure for interoperability, I'd say, with Courtney Peverly giving us an overview of the CCPP. I'll let her define the acronym.
Oh.
I heard it on one of you guys.
No more squids.
Yeah.
Can I make this?
Oh, sorry. Yeah, there should be. Should be. Otherwise I have. You know what?
Could do
It's might
this.
work better for the download.
Okay. All right. Hi, guys. I think I know most of you in the room, at least. If not, hi. I'm Courtney Peverly. I'm a software engineer here at NCAR. I work in CGD mostly. I work in on CAM, also the CCPP framework. And I'm going to let my slide define it for you. No, I'm not going to say it. I'm going to read it. So if you attended the summer working group meeting, it would. You heard Jesse give a talk that included this slide. This is just some table setting because what we're going to talk about is that guy. So this is just an overview of how CCPP framework interacts with the host model and the physics schemes. So this is where you can find the code. This is the repository link. There's two key branches here. There's the main branch, which contains CCPP pre-build, which is currently used operationally by NOAA. And then we have feature caption, which contains caption, which is what we use in SEMA. And the goal is to get caption merged into main. Dustin Swales and Heinzeller, who you heard from earlier, have been working hard on getting that merged in. And that's what we call unification, if you've ever heard of that. So this is kind of a class diagram of caption. It's not extensive. There's other stuff happening. I'm not going to go into crazy detail. Turns out it's hard to find a line of how into the weeds you get in this stuff. So feel free to tell me at the break if I fail. But I just want to, it's a software group. Let's see some software design, right? But please feel free to zone out during this section if you'd like. Big bold arrows are class inheritance. And if you wanted to jump into the framework, I'd probably suggest you start at the API class, which is kind of the organizer. And basically, we'll see this go in the future, but we've got suites, which are like the highest level of organization. And within suites, we have groups, which are special schemes that you can follow their run phases at separate times if you want to do something in between those. And then within each group, we have a set of schemes, and those are that's actually the code that's developed by the developer that the framework is generating the caps for. You'll see that each of suite, group, and scheme all have an analyze and a write routine. Those I see as kind of like the key elements. Basically, the analyze routines kind of do all the table setting for the write routines, which is what actually generates the caps. You can also see on the side, we have some objects that deal with variable compatibility. So Dustin Swales implemented those to enable automatic unit conversion, which we'll get to later as well. Like I said, probably too in the weeds, but I could have gone further, so you're welcome. So here's a little example. On the side, we have code generated by a human, or I guess an AI in theory. And on the right side, we have the code that's generated by the framework. So the top left is an example of a suite definition file. So that contains all the information the framework needs for the suites, the groups. So in this case, we have two groups within our test suite with really excellent scheme names, if I do say so myself. And then underneath there, we have a header for each of our schemes. So every scheme has to have a run phase, because otherwise, what are you doing? And but you have optional phases as well. In this case, the Courtney scheme has an init phase, and the Peverly scheme has a time step final phase as well. So that, combined with all the necessary metadata, leads us to generate, among other things, these two Fortran files. The host CCPP cap. So the word host will vary depending on your host model. In CAM, it's CAM. And then, so the host model is going to call these caps. These caps will always have the same name. And then within these cap routines, they will call our suite routines. And within those suite routines, what the framework's going to do is it's going to make sure it has all the necessary variables to call every necessary routine that we have. So what it's going to do is it's going to say, all right, within our suite, do we have any init routines? And if this, remember from the left-hand side, we do have one init routine. So my suite initialize is going to call Courtney init, and then time step init. You don't have any time step init routines. So that's going to do nothing. And then we have two different run phases because we have a before coupler and an after coupler group. So the before coupler group is going to call Courtney run. The after coupler group is going to call Everly run. Time step final, we do have a Peverly time step final, and then we don't have any finalized routines, so that's going to do nothing. So that was a overly detailed explanation, but there you go. That's how that's how the code kind of works without going again into way too much detail. So within the last year or so, we've had a few new caption features implemented that are important for unification. So the first one is constituents. So this is an object for the handling of constituents in caption. So what you can do is in your metadata file, you can specify an attribute that tells the framework that, hey, this variable is a constituent, and that will tell the framework that, okay, I need to handle this guy. And so the framework will handle that variable and allocate it and all that jazz. There's also, which is in progress, and if you go looking for it in the future caption code, it's not there, but it's in progress, is the ability to define constituents at runtime. So if you have a scheme that doesn't know what all of its constituents are until it reads it from a file or something, then you get to write your own fun routine that returns all the constituent properties, and then the framework will incorporate those into the framework object or constituents object. And then from the user side, you can then use the constituents by either passing in the full array with that standard name CCP constituent. So that gives you all of the data for all of the constituents. And you can just loop over that how you see fit. Or if you just want one constituent, you can specify the specific standard name for that constituent, and that it'll just grab just that data for you. There's also, you can see in the code snippet at the bottom, there's a constituent metadata array. So that also is can be accessed via the CCP constituent property standard name. So that's going to contain all the information for each constituent. So that's whether it's infected, whether the units, is it mass mixing ratio, is it a water species, all that fun stuff. And so if you only want to conditionally act on some constituents, you want to grab that as well and then have some conditionals in there. Another new feature was implemented by Dustin Swales pretty recently. And so this is what I referenced earlier with the compatible class. And so that's automatic unit conversions. So the infrastructure is there, but we only have a limited suite of conversions available. But we can add to that going forward if someone runs across something that isn't there, like a conversion that isn't there but should be. Here we have an example. So say in, this is from Kessler init, you have this prefin variable and the units are specified as pascals. But oops, our host model has that same variable, but the units are hectopascals. The framework is gonna declare a temporary variable, prefin local, prefin local, and then it's gonna do that conversion for you before passing it in, and then it'll convert it back. In this case, it doesn't do that because we never use prefin again, and so it's smart enough to know that it doesn't need to waste its time doing that. And then if in the case you had units that weren't compatible, like you try, trying to convert fingers to toes or something, then you're gonna get an error that says incompatible units, fingers to toes. So you're gonna either have to like rethink your life, or you're gonna have to make sure those units line up, and then so you'll get a useful error if it's not there. Or you can try asking us to add that conversion. Good luck with that. Okay, so that's pretty much all I have. I may have a sped run through that because I'm in a panic. But any questions?
So I think you have a pretty well-defined API for host models to call CCP, right? Is there also an API at the lower level for integrating I forgot your terminology. Is it suites?
Do you want me to go back to the?
Yeah,
full class?
schemes.
Schemes? An API to call schemes directly or?
Well, so you've got a scheme that's been used in some model for years and you want to add it to CCPP. Is there a clear way that you would do that?
So assuming it's CCPP compliant, which is a big assumption, but assuming that's the case, then you just would add it to one of your groups in the suite definition file.
Okay.
And then the framework will do its work, its magic.
And then one more question, and there's a lot of interest, it seems, in moving away from Fortran into other languages. Is there capability for language interoperability here?
So there's the ability to use underlying CCPP code if you build a Fortran app for it. I mean, that's always been there. And I think that there's long-term plans to have a CCPP writer option, but right now it's purely Fortran that we're generating. So who would prefer first?
Yeah, I have two questions. One is the automatic unit conversion, because this is the central piece of our system modeling. So is this tightly integrated with the CCPP at this point? Are you planning to extract that module and make it available for other use cases? Because, for example, for ESMF, we are exchanging the data between the components and the units could always different. So is it possible, if you make it generic and then usable with the other tools, and then maybe you can plug that tool to ESMF, and then when you're exchanging data between the different components, you can use the same tool.
That's really smart. And we've talked about, instead of making ours more generic, using an existing generic kind of unit conversion suite, so we don't have to implement them all ourselves.
Yeah.
But as it stands, it's pretty specific. Like there's a file that a module that has all of the conversions that are parsed by the frameworks. It's not super generic, but I think that is a good idea in general. Whether we will do that or we will use someone else's generic option, I'm not sure.
Yeah, I had other questions, but I forgot.
I saw Eric next.
Okay, first of all, I love that you showed some design work. That is awesome. And I love to see the code this is just really cool, by the way. I'm really excited about this and that you're doing this. So the other thing I wanted to ask about is the build. I'm just kind of curious how that works, because you're going to create Fortran code, which I assume you're not saving in a repository. It's probably just being built at when the make file runs. Is there like a CMake thing that makes this whole system, or how is that?
It is a
done?
CMake thing. Basically, it's at least in the host model CAM specifically, it's being run at like preview nameless time. So it's like run before the build, and then the build runs, like the build then continues on from that.
Oh, really? Okay, so it must be pretty quick.
Yes.
Yeah, that's
It's
cool.
not broken. It's quick.
Okay, awesome.
I think I saw Bill next.
I'm asking on behalf of Peter Lauritsen from online, who asks, does the CCPP framework support parallel in time physics, meaning where all parameterizations start from the same state as is done in WRF, in contrast to CAM physics, which is sequential, where each parameterization updates the state, which is then passed to the next parameterization?
Oh, we're getting out of my knowledge here. I think what it does is I think it's sequential right now, but there is, thank you, Dom. You wrote the thing.
If it's okay, right now it's not automated. The way this works in the UFS, for example, we have both. We have one part of the physics that update the same state based on the same input state, and they just return tendencies. And then we have a bunch of physics that update the state and return the new state. But that's more or less hard-coded but it depends on what you feed in and what you send back. So it's not automated yet. In Capgen, there is the concept in the framework of a time split versus process split. But I think there is more work that needs to be done until we can really automate this, because you would have to analyze the scheme, know what the scheme wants to do, and if the scheme returns the state in place or updates the state in place, but you want it to be process split, then you have to wrap this thing by capturing the initial state, reset it afterwards, and compute the tendencies from the difference.
Yeah, this is something we're running into a lot, which is the more we add to it gets really complicated, obviously. Yeah, Mike.
So this is two questions, kind of follow-ups to Eric and Ufuk. So when, like, you have the slide where you show the human-generated code on the left and the CCPP, like what language is actually making
It's Python.
Python? And then on the unit conversion,
Mhm.
like the code you wrote to do unit conversion, what language is that in? Like, is that still in Python? Or is
Still
that
in
already?
Python, yep, it's just generating Fortran.
There definitely are unit conversion packages. I can't remember the name of the one that MetPy uses, but
Yes.
I've had good luck playing with that one.
Yep, that's the thing, something we talked about like a week ago. So yeah, we're definitely thinking about that.
Plus another online question from Dylan Dickerson, who says, great work. Follow up to the quick build. Any stats for how quick generating the Fortran files are, and are there any other impacts to the build time?
Wonderful question. I don't have any statistics on that. I just know that as someone who builds CAM, it's nothing compared to the actual CAM build time.
Yeah, it's good.
Yeah.
So for the unified forecast system, it depends on the number of suites and schemes you have, but
Yeah.
for the UFS with all the suites, it's like 20 or so of them. The pre-built script, which is comparable in runtime to Captain, maybe a little bit faster because it's less, less beefy, runs in maybe with 10 seconds, something like that. And it generates Fortran files. And one of the things we had to do when we implemented this first is make sure that the Fortran files are bit for bit identical every time. So there can be no difference in terms of order where variables are defined, even though for Fortran it doesn't matter. But for the build system, it matters. So we write the files to a temporary file, and then we compare the temporary file to the file that has been compiled beforehand. If they are the same, we throw the temporary file away. And if it's different, then we overwrite it so that the build system sees the difference.
Cool.
Yeah.
Very minor question. So the CCP basically depends on the host model, and the physics is basically using the same grid with the host model.
Mhm.
Is there any plan to implement an additional layer to run the physics in a higher resolution? Because for the lens, you might want to run higher resolution.
Not that I'm aware of.
Yeah, at this point, I would say that didn't bubble up as a, top priority. I mean, it has been talked about a lot, but there's no development happening there. There's some development happening in terms of generalizing, so it's not so column-based, but it can see halos around the columns. And yeah, that would probably be happening in the interface with the host model, not in the column physics itself.
Yeah. Okay. Yeah, I just wonder.
Thanks, Leisha. All right. You good? Can I leave?
All right. All right, we have one more talk before the break, which is from Christina Hull. And this kind of continues in the, I don't want notifications, continues in the theme of collaboration between CESM and UFS, so NCAR NOAA collaboration, either kind of current or for potential future. I'm really happy that Christina is here to present and tell you about the unified workflow for the UFS, and I'm hoping to still kind of look for areas that we can have some CESM and UFS collaboration on this. So thanks for coming.
Make sure that I don't trip over things.
Sorry,
Bad luck with that lately. Okay. Oh gosh.
Yeah, do it again.
Did I get it? So I am speaking today on behalf of the whole team at both NOAA, GSL, and the Earth Prediction Innovation Center. We do make up an Epic Agile team. They use the Steel Agile framework to run a whole train of teams, and we make up one of those. And we do welcome contributions from various different funding mechanisms and that sort of thing alongside Epic to unify the workflows across UFS. And I really appreciate that Dom went first today to give y'all an introduction of UFS, because I skipped that completely. So we'll draw on a little bit of that knowledge. So at GSL, we have 4 of the 6 team members who are funded either by a JTTI or SENA, which are just NOAA-based funding mechanisms. And those are aimed at giving us some unification across the short-range weather app, as well as a distributed workflow that we're working on that works across various different platforms. And then we have Epic contract support here with our partners from Raytheon and Element 84 staff. Now, of course, the main goal is unification, and that's the one that we work toward most hands-on with making sure that multiple apps can use the same tools to perform the same tasks. And that's the very basics of the unification that we're going for here. We also want a side effect of easy use for flattening the learning curve, so that when you do start using a UFS app in one area, you might be able to translate that knowledge to another app for hurricanes or something if you were starting with short range weather, or even going to the global workflow. Flexibility really is another key side effect of this. We hope to be able to empower our scientists to realize the experiments that they want to do without being limited to some of the workflows that already exist out there. And then, of course, facilitating R2O is a big thing within NOAA as well, so that we can get research and operations using the same, I mean, they're already using the same components, but then having them use the same languages to configure and run those components is also pretty important. This is not a new concept that I'm presenting today. Back in 2021, Hendrik Tolman presented this slide about his ideas of how a unified workflow could look. And I'd like to report today that we are well on the way to getting this library that he called it way back then, where we have a runtime configuration where you have standardized naming conventions that work toward automating combinations of these different components. And then a scripting layer that standardizes the execution of those components. And then we have the components themselves, where they typically have a pretty strict, unchanging, for the most part, interface that allows us to configure them and run them on HPC systems or the cloud. So this library area is where we're functioning, or where we are aiming our efforts, and then we are really just interfacing to tools like Recodo for our workflow management at this point. So the software that we're developing is a Python package that provides a command line tool set and an API for Python, so that you can perform common workflow tasks and drive UFS components, just like we were talking about. And those are the 2 things that I'm going to try to introduce today, and leave a couple of other things out. But we do publish this with each new release to the UFS community Anaconda channel, so that you can easily install it. And we are planning, and currently in the middle of, integrating some of these tools to different UFS applications. And currently we're working on the short range weather due to that JTTI funding, and then LandDA is an epic effort to get the JEDI-based standalone land data assimilation system integrated with the UW tools. So we're currently at version 2.0.1, and you can install it with a one-liner here if you're using Conda environment. And as soon as that's installed, you have access to the command line tools that start with UW, and then we have modes and actions under that, just like you would see with like Git or Conda itself, having multimodal options there for you to use. We also have the API that's limited to just the bits that we want to support exposed to you through our API. So you can import that into your existing Python codes. We also have all of our code on GitHub here and extensive documentation and examples on Read the Docs. I do just want to start with that command line interface introduction here, what this looks like. And then we do have a lot of API equivalents that kind of map to the same things here. And this is just a subset of what we currently have in the latest main version on our repository. But like I mentioned, you get that one interface in the command line. You have a mode as your next argument there. So it could be configuration, templating, interface to our Rakoto workflow manager, or one of the drivers like forecast. And then that next entry is going to be a variety of actions you might be able to take under that particular mode. Each of these levels then has a help flag, of course, so that you can see what your next option set would be. So each of these might have a whole set of flags that are necessary for them to run what you would like them to. So I picked a couple of the tools to talk about today that might interest y'all the most. I think that is a good way to start talking about the very generic things that we're doing, like configuration management through our config tools or templating. And then I'm going to jump over to some of those drivers. So here we're aiming at providing a set of tools that allow you to compare, transform, modify, and validate any of your key value configurations. So that might be YAML, Fortran name list, any or batch files, so that YAML then can become a universal language for interacting with any of those files. So this one's my favorite, just to be clear. We do a lot of cool things with name lists and YAML and all of that stuff, but I really hate running two different name lists through Linux diff and then figuring out what to do next. So this one just gives us a nice clean interface around how two name lists actually differ. And so you can see here just one file, then the next. And so I like to show this one off every time. But this is pretty cool too. We have a realize mode, which does a couple different things here and varying levels of how you would like to interact with it. But let's talk about an input file that an application might save defaults in. A user may never have to interact with this one at all, but you can do calculations and things directly in the value of the base file using Jinja templates here to do some math based on other information that you do have set to a particular value here. And then one additional step then allows a user to apply a supplemental file on top of that, so that all of this gets realized and all of these values get updated so that our output file is the one that you're ready to use in your system. All of these values are filled in with the math. The user gets to update any of these key value pairs that they like in here. If they wanted to call it my favorite forecast instead of run forecast, they could do that with just that additional input file. I will move along to templates. You've already seen a little bit of this, but we are leveraging Jinja for a Turing complete option for templating all of those files and their values, but also just flat files. It could be a letter to an editor or whatever you want that gets templated, but we are using Jinja here. So all of our tools have really nice interoperability with Linux file system, or sorry, a Linux-based system, so that we can read from standard in or standard out and pipe a bunch of different ones together. But even if you just want to see if an entry would work, which is what I was doing here for slicing up this string, it's easy enough to just check that really quickly on the command line. Another cool thing that Jinja gives us is if you have a big long template and you're like, I really don't want to go through this today to figure out what I need to put in this configuration file, I just don't have time for that, it will tell you what values you're going to need to provide to fill in the template completely. One other way that we're using this is to completely render from variables and or value files. So you could store cycle and DT Atmos in the environment or in a file and get this this printed out as a fully realized or a fully rendered template. Again, with Jinja being there, you can start to do some really nice things. It is not just a substitution of a value, but even putting your logic in there to say, sometimes I want to run a longer forecast than others, and it knows how to handle that for you. So that's all the introduction I wanted to do with the more generic components, but I do want to talk about the graph-oriented approach that we're taking for drivers, which I think is pretty cool and not something that we see very often in the existing systems that we have here. So if we represented a basic Fortran program as a in the preparation to run that as a graph here, we could represent each task that you need to do up to execution as a node in a graph, and then the dependencies are represented as those edges. So if we wanted to run a Fortran executable, we would need a provisioned run directory that might include a run script, data files, and a name list file. Those all, of course, are independent in this use case that I'm presenting here, and you would need a run directory to put them in. So here, we're talking about giving you access to some component that you might want to run, and we'll support specific ones for UFS and give you the capability through the API to generate others that you might be interested in that we don't support, and then call any of those nodes in the graph to just generate that thing without necessarily running everything. So if you wanted a provisioned run directory, you would have an argument here to do that. If you just wanted to see a fully realized name list file to make sure that it's configured the way that you think it should be, run it past some collaborators and continue on, we'll give you that option as well. Or maybe you just need to stage data for that particular thing. We're using the IOTA Python package to do this. It's been developed and maintained and is currently maintained by Paul Madden at his GitHub site here. He's named it It's One Thing After Another, which I kind of like, for a workflow manager. And it really does just provide us with a workflow engine, and we're treating each of these individual components as a little workflow so that we can express those using Python code and make it responsible for readying the asset that they need to be successful in the next step. And then also it gives us an opportunity to define the relationships between these different tasks. So what you get with this package, and this is a very basic introduction to this, check out his really nice examples and documentation at the website, but we have a bunch of tasks in a workflow, right? So this is how we would represent a node in that task. If we wanted a nameless file, we can define a function or a method in Python, decorate it with task, which comes from IOTA, and then we need to yield 3 different items within this function, where we get the asset name that is meant to be prepared by the task. We'll define what the asset is. So in this case, it's a name list. It needs to be at a path called input.namelist, and it needs to be a file there. And then the requirements for being able to make that task ready is that there needs to be a directory there. So then once all those are yielded, we can talk about how to complete the task to make that asset ready. There's a lot more that goes into this, but I really like this very simple interface of Python code that lets us define specifically what we need for this task to know how to complete. The benefits of setting it up this way include composition. If we look at each of these more complex tasks or complicated tasks, we can start to break them down into smaller things, like just a name list, just some data files, just some other input config files. If there's a ton of those, like there might be for a couple system, it becomes a little easier to see which component requires which files. We also have selective execution. Like I mentioned before, you can choose any of the nodes of the graph and just do that thing in any of the things it depends on. You can iterate over a given driver until all the tasks are complete. So maybe some data wasn't ready the first time you ran it. You can run it again to check on that data without having to run everything else in the graph again. Or maybe you found an error in an asset. You can just remove that file, that asset from your run directory and run this thing again, and it will recorrect it if you made some modifications. Idempotence is another good one for this. We don't have to run those tasks again. It saves resources. You don't have to worry about overriding a file that was good in the previous iteration that you maybe edited. And then self-healing is another natural outcome of this. Did you accidentally delete a file? Happens to me all the time, but run the driver again so that you just get it back without having to panic and run the whole thing again. So in summary, I just wanted to close with a reminder that UW Tools is actually at a point where it's a tangible Python package that you can go get, and I'm super excited about that at this point. The tools are designed to help scientists be productive and to help applications increase the automation of the common tasks that often lead to more brittle code. The graph-oriented drivers, I think, are more flexible than many of the existing solutions that we often find are hard-coded in their procedural style and may end up brittle for that. And I think that this general approach is going to help us with hierarchical testing on the research side and also help with reliability and recovery in those real-time use cases that we also are aiming at in the research to operations transitions. We do have some upcoming plans. We regularly want to be releasing new tools and drivers. So regularly here means probably once per program increment with that safe framework. So every 10 weeks or so, if not faster. Bug releases come out as quick as we possibly can. But those new tools and drivers come out a little less frequently. We are integrating UW tools into the existing applications and plan to continue that. We have several drivers up next that we would like to integrate with, and then a couple of additional generic tools that we'd like to add to the toolbox. So that in the end, we have a nice set of tools that may wrap a whole bunch of different UFS components here and give you just the interfaces that you need. So I'll leave you here with the acknowledgments from all of the different groups that are helping to support this effort and take any questions that you might have. Thanks.
Well, that's a good question. First of all, thank you. This is some really cool stuff that you together. Look forward to looking more into this. Thanks for highlighting that. To bring in a new component, let's say you want to integrate FP3 into the workflow, or some other component into the workflow. How much is needed, if at all, sort of changes within the sort of component repository, and how much would you do within the unified workflow and code base to integrate with a new component, describe the configuration files needed in that sort?
Sure. So at this point, we haven't made any modifications to any of the UFS components to have supported drivers. So this is really just taking the place of the scripts to get the component ready to run. So we don't have many goals in changing those things. We have maybe a couple of small ones that could be done better in FP3, but they're not necessary. We have the tools to support it as is. As far as the effort to integrate a new driver to our code base, we are early in the stages of that, but starting to see a really nice pattern that helps us move more quickly to get those integrated. So as long as one of those is already integrated, then it's as easy as checking it out and using or installing it in your conda environment and using it, or building it from our main. If you wanted to create your own driver that you did not want to put back into UW, we haven't gotten to a use case like that just yet, other than me playing around and not putting my work back in. But I think our API would help support that kind of effort. And I think that really it does come down to, you know, if you already have a Python script that does all of the steps, then it's just breaking it down into those tasks with those decorators and things to define the workflow. Sorry, I don't know names as much as.
Oh, that's fine. I'm Eric, by the way. Nice to meet you.
Thank you.
Awesome. So I'm not quite sure your terms. So you use the term driver, and when I think of driver, I think of the Fortran code that's at the top of CSM that drives all the models. And that's all done using ESMF and nuopsy, which I think you're not talking about that, but I think you're talking about you know, input processing and all the stuff that you need to do around the Fortran driver to get things working. Right? And you're shaking your head, so it sounds like, can you elaborate on that a little bit?
That's right. So we often would hear run scripts or, you know, even batch submission scripts. Our drivers are going to be kind of taking the place of what that would originally have been in many of the other systems. So driver is kind of the word that we landed on, but, you know, with this overloading of terms that we have in this space, I'd be very happy to take other suggestions. You know, we're early enough that messaging here is pretty important. So if driver doesn't make sense, I'd definitely like to talk about terminology.
Yeah, awesome. And so a follow-up to that is you used the term graph-oriented.
That's right.
Driver, and I'm not quite sure. So this is graph-oriented versus hierarchical, or?
Just more procedural in terms of the design of the code base. So typically, we would have, you know, one thing done after another. Make a name list, link your files, and execute the program.
Right.
So, and every time you run that script, you would run every single one of those things.
Yeah, right.
So this is kind of the context that I'm coming at graph oriented here. So that we are defining each individual piece of work as its own individual thing, and we can then reach into that part of the graph to understand what's required to achieve success at that level.
Oh, okay. Okay, cool. So the interdependencies and that sort of thing, and the ability to just do one node rather, because everything else is done.
That's right.
Right. Okay, cool.
Yeah, I have just one question. So, as I know, at this point, it's just used by the standalone FP3 or something like that, right? So, what's your plan about supporting the very basic coupled application, for example, data ATM for some ocean component?
That is something I should have added to that last slide. Maybe I just skipped over it when I was saying it here. So right now, because we have that program for the program funding for supporting short-range weather, it's a standalone limited area model that we started with. But we do have plans there to move toward supporting global as a configuration for FE3, and then of course coupled. That's going to come down to starting to have a composition relationship between various different drivers. So we're going to need to put a little bit more effort into that design and how we actually want to handle that. So somebody's going to be somebody has to be responsible for that coupling file that goes in the run directory, and then individual components then would be responsible for the data files and the configuration files that they would need to be successful in the coupled situation. So we're aiming at a bunch of individual standalone drivers first, and then working up to a coupled.
Is it possible to easily implement, for example, the driver for example, CDEM's data atmosphere?
A standalone model, is that right?
Yes, okay, not standalone, because in the short time frame, we will start working on the UFS coastal workflow. The initial aim is to create a very simple application coupled with the data atmosphere and or.
Okay.
So that's the short-term goal for the UFS coastal, and then I just want to learn that we can achieve that goal in a short time. For example, maybe in the next 6 months, can we have that one under this tool, or?
I would hope that within 6 months, we definitely have a nice design for how to get coupled components together there.
Mm-hmm. Yeah, that's great.
I tried to bite my tongue, but I can't help it. All of this capability is already handled by the SEAM case control system that UFS rejected several years ago.
Right.
Just
I will say that was far above my head at this point. And in doing research for this package, I do want to give a shout out to SEAM. Like, that code is so nice to navigate, check in on how things are working, and it really is a nice code base.
And I think, you know, one of the things that I still hope for is that we can find areas here of collaboration and things that we can pull out of each and do things together, so that we do try to reduce duplication of effort, at least moving forward.
I think it's good to say that it also does not have full adoption also yet. It's a work in progress, and like how to infuse this nice work, just like the case control, into the applications and the scientists' work, they're doing work every day. It's not obvious, you know, and so full replacement seems to be harder, as opposed to starting like, put this tool in, put this tool in, and try not to be very disruptive to the work that they are doing. So I think there's like a difference in the culture of like how we're trying to approach integrating the unified workflow than what happened with the case control, which wasn't just about the software that it didn't go through. There was this cultural full replacement.
I do want to suggest that we've had or at least bring up that we have had a couple of conversations about the idea that if we could package SEAM, I don't know if this is the current state, but if we could package SEAM and use various different components out of there, then we can kind of essentially use that as the back end of like this front end that we're doing here, so that we don't have to duplicate those efforts. We've had conversations around the way that configuration files, help me with the name of
the CramGen, using CramGen.
So those types of things coming into our, I'll call it back end, so that we have a similar kind of command line interface to access that kind of utility, would be a fantastic way to bring in some of the great work that already exists out there from the in-car, U-car side, and get that added.
I could go into this, where there's more duplication of efforts when it comes to the JCSDA workflow and things, but we'll skip that for now. I wanted to ask another question. I see EasyFlow interfacing down here at the bottom.
That's right.
Is there a plan to support Silk in addition or instead of EasyFlow? So all we've seen is that Silk is far superior to what EasyFlow provides, and there is a motion on our side that we're probably going to move over at some point. Actually, went the other way. Jim is saying he's going the other way.
I went the other way from Silk to EasyFlow because of the Jupyter
Yeah, it's gotten
problem.
Yeah, but it's gotten a lot better. So that's the point. You know, they have abandoned the old Python 2 interface. Everything is Python 3 now.
As I'm gonna say, this is probably a good conversation to have during the break. I want to keep us on track, so I wanted to make sure we get some lunch before the rest of in-car goes.
I love this conversation, though. I'd like to.
Yeah, let's definitely have more of it. Yeah.
Thank you.
All right,
All right.
So let's take a 10-minute break so we can then get back on schedule. So back at 10.
Yeah.
Thanks for taking me down.
Maybe it'll try to show up in person more.
Hey, we're back. You can hear us now.
All right, welcome back. We have, we're always interested here in keeping up with our tools and techniques. And so along those lines, the next step is we have a set of presentations on Visual Studio Code. Initially, we'll have two kind of back-to-back joint presentation. First, Adriana Foster will present an overview of Visual Studio Code, Visual Studio Code in U, and then that will be followed by Sam Raven, who's going to give a demo, and I think it's sort of a joint thing between the two of you. We will pause after Adriana's to take some questions on hers, and then transition to Sam's.
Nice. All right. So yeah, so VS Code in U, this is kind of both about IDEs and how you should think about using more IDEs in your life. So for the uninitiated, what is an IDE? So it stands for Integrated Development Environment, but it's basically just software that helps programmers in their code development process by combining software editing, building, and testing. And so, but essentially what I kind of my thesis is that this IDEs kind of help you speed up your everyday coding tasks. And so think of it more like Google Helper. So I thank you to those of you who filled out my survey. I sent out this survey ahead of time because I was interested in IDE usage within the CGD. And so this is the results of the first question, which was asking folks what they use now. It's just the dots are individuals, and the colors are scientists for red, blue for software engineers, and purple for a mix of both. So we can see a lot of scientists said, no, really, what's an IDE? A lot of people actually use Sit Here, which is like a text editor with syntax highlighting, some IDE usage, and then I'm just going to call out some individual people. That's Michael Waxmaxky, and then here's Bill, who says some IDE usage, and then Dan said, I don't know, this was his response. I'm not sure, I wasn't really sure where to put him, but I stuck him somewhere in the middle here. All right, so okay, I'm going to give you a brief pop quiz. If the first person to get it right in person, sorry for those online, you get a Kit Kat. What is 5,772,513? Oh, you have 3 seconds. You want your Kit Kat? Come on.
About 1,300.
You gotta get it right.
1,279.
That's right.
Yay.
Ooh, he's
You
close.
want division that quickly?
No, I used a tool.
Oh my God. Okay. All right. I'm going to posit that using an IDE is like using a calculator, right? We could have done long division, but that would have taken us a long time. And we also may have gotten it wrong, right? So, okay. So I have another scenario for you. We'd like to rename a defined type. This is from the Fates code base. We have this type called Fates cohort type. We don't like that because we just want it to be cohort type now. It's obvious that it's Fates because it's in the Fates repo. So, and I just did a grep. There are 196 instances of Fates cohort type within the Fates source code. So we could do this by hand, or we could have our IDE do this for us. So here I am highlighting the rename symbol. This is VS Code, changing it to cohort type. And it's nice here. It says Shift Enter to preview. So it's thinking. And then when this is finished, it's going to pull up a kind of preview of all the instances where it changed. So we can run through and check. And at the end of this, we can say accept or abort. Okay. So yeah, what can IDEs do? So at the bare minimum, they give you syntax highlighting, which I'm going to show is nice. There were some people who said they don't use syntax highlighting, which I think is crazy, but okay. So we can also get some more fancy things like code auto-completion, refactoring support, code navigation, which is really nice for our complicated models that we have in CESM. And then even fancier, we get build, execution, and debugging tools. And then some, extra features like source control, GUIs. And then a lot of this is based on linters, which if you don't know is just a tool to analyze code. So linters know, you have a linter for each specific language, so it knows your language syntax. It can help you optimize your code. It might give you little hints, say like, hey, this thing you wrote stinks. Let me help you fix it. It can find typos and syntax errors, like if you forgot a and sign or a comma. It can warn about unused variables, and then it helps to conform to language or source code standards. So often you can set up your own source code standards that you want the linter to look at. So, okay, syntax highlighting. Here an example of 3 different, basically the same thing. I have an array, the size of the array, in 3 different languages, Fortran, Python, and Java. And when I look at this, I'm like, I don't know I have to actually read. I don't want to read. But with syntax highlighting attached to a linter that actually knows your language, you can, I would say you can much more easily tell at a glance what's going on. So if you're not even using syntax highlighting, I would say at least get yourself to that level. Okay, code auto-completion and documentation. So for code auto-completion, a lot of linters and IDEs can actually help you auto-complete code. So here I am again in the Fates repository. I'm going to add a function call and it's saying, oh, you want site history? So I just tapped complete, yes. And now it's pulling up with the actual variables that go into that, this function call. Here I am typing. So this is really nice because, I don't have to loop back and forth and say like, what are the variable names? And then so it's both kind of helping you write faster and then also kind of, you're like kind of checking yourself while you're writing it. So I find that really nice. And then a lot of these are string. But if I'm going to pull up a actual, oh yeah, I forgot an ampersand. I would have gotten an error, but all right. So yeah, so add flag, those things are all like variables that exist, and then we're pulling up B type. Yeah. So I don't have to like remember all of these variables exist in my code base, which is nice.
Yeah.
There's also documentation. So if your functions have documentation, which they should, if you hover over a variable or a function, it will, VS Code will pull up this little window that shows you documentation for it. So I'm hovering over this function isDear, and it's saying, okay, this takes a string. It spits out a bool and returns true if the path name refers to existing. Actually, real world examples from GitHub. And then what I find super useful is code navigation. And so with kind of our really complicated source code that goes all over the place for CESM models, you can actually hover over subroutines or functions, and then you click them, and it will actually pull up a tab for where that in the file, and then it takes you to that function. So here I'm in decomp because I pulled up bounds type. And I know like Emacs can do this too, but the really nice thing about having the GUI is that your tabs are all still there. So you can just go back and you don't have to remember a keystroke to go back to the last place you were. And then I'm going to take a quick detour to PyCharm because I find that in terms of code refactoring, meaning that the code can actually, the linter and the IDE can actually say, hey, your code can be better. Let me help you fix that. I found that with Python, VS Code doesn't do a great job, but PyCharm, which is kind of this dedicated Python IDE, does really do an awesome job. So this is looking at in a function that I wrote, and there's like a little yellow thing here that says, hey, something's wrong. So it's saying, hey, I think get batch query might be static. So this is currently inside a class, and it says, well, this isn't doing anything to your class, so I think this is actually static. So do you want me to fix that? Oh, do you want me to fix that for you? Mm-hmm. And so I say, yeah, make function from method. So now it's disappeared. And then if I scroll up, there it is. So it's new. Now it got rid of the self. It's doing the same thing, just now a static method. So pretty cool. So yeah, PyCharm can do a lot of stuff like that. It'll a lot of instances where it'll just completely refactor your code for you, and it works. Okay, and then the other thing is building, executing, and debugging. So you can build, execute, and debug code Fortran from inside VS Code. And we do this via this .VS Code folder that you would put inside any workspace that you're using. So workspace would be like, for me, like I'm inside the CTSM repository, my local. And so I would create a .VS Code. And then inside that, I put these two JSON files, launch.json and tasks.json. And so tasks.json, for my use, is for automating everyday tasks. And so as an example, I made this create task, which creates a CTSM case. And really all it does is kick off this create test case bash script that I wrote. All it does is just, do the normal case.create scripts using a config file. And this config file, I've actually set as a script argument. And so VS Code is really cool because you can actually have input arguments that can either be buttons that you click or strings that you type. So here's just looking at the inputs. And so here it's a pick string, which means VS Code is going to show you 3 different things. I'm going to click one. And yeah, so here I'm going to just, show you. So here I am at the top. I'm going to say create. Now it's showing me, which one do you want? Oh, do that one. And then here, yeah, you can see it runs. Yeah, so it's been super useful. And then in terms of debugging, that's when launch.json becomes useful. So for here, all you really need is the CESM executable, and then you tell it to run it in the run directory. And then if you also notice, I added this input case steer as a variable input. And so using this, I can basically have VS Code ask me, like, which case do you want to run? And so it's just the full path to your output directory. So it'll run this executable in this run directory. Yeah. And then I just want to show a quick, I just wrote a silly program to show you the debugger. And so this is just a little program that is supposed to print out the Fibonacci sequence using a random limit between 1 and 10. So here I'm just going to run it. Nothing's happening. That's annoying. What's happening? Okay. All right, let's see. This really exists, right? Yes. There's the program. It exists. All right, let's debug it. So we're going to click there. That's setting a breakpoint. And then over there, I'm going to run GDB. Okay, so now we've stopped at this breakpoint. The limit is, oh yeah, so it hasn't been run yet, so the limit is garbage. We're going to push, there's this little handy dandy navigator for the debugger. That means step over. The limit is 0. It's supposed to be between 1 and 10. That's annoying. Okay, let's start over. Rerun. Okay, here we are back again.
We are 14, okay.
Okay, and then we're going to step into the function, right? We're calling random number, which is this intrinsic, step over. Wait, I thought random number was some integer number. No, it's a 0 to 1. So that's why I is 0. That makes sense. Okay, so anyway, we could have used print statements, obviously, to do that, but that takes time. It also takes compile time, which, for this program is cheap, but for something like CESM is pretty expensive. And yeah. Okay, so some other stuff, you can customize your editor. So if you hate black dark mode, you can change the theme. There are guide bars, so you can, if you say I don't ever want to code, past 80 characters, you can set up custom guide bars. It has really nice interfacing with Git. There's like a mini map on the side for scrolling if you want to set that up, so you can scroll and it'll show you like a little magnifying glass of where you are in the code. And then over here is just showing the source control pane, which is really nice. So this is looking at the source control, so the actual files. And then if you look at the outline, that shows you your actual objects and functions inside whatever source code you're on. If you are an Emacs or Vim enthusiast, there are emulators inside VS Code, so you can get all the features of VS Code while it still feels and looks like Vim. And then remote SSH, which we used a little bit during this talk, lets you to actually connect to a remote server like Derecho. Sam is going to show a lot of GitLab stuff, and then there's just tons of extensions that you can download to just really make your life way easier. And then the last part of the survey was, what are you like, sort of, how do you feel about your knowledge of VS Code or IDEs? And so almost 50% of people said that they wanted to learn more so they could update their current process. So that's great. And I hope that this has piqued your interest even more. And yeah, and I think Sam is going to show. All right. Thank you.
We'll take some questions on this. Well, how do you want to present it before we transition? Yes, Tim?
A few slides ago, you had a variable that was a pointer to the case directory.
Yeah.
Could you just use the XML that's already defined?
Oh, here?
Yeah.
So this is inside VS Code, so I don't know about that, but that, yeah, that's a good point. Possible.
Me?
Yeah.
Okay. Just okay. So I've been working through various debuggers for a long time, like TotalView and DDT. And how have you used this one with a parallel, like with CESM? Like, does it work with a parallel while running on the batch system?
I haven't tried, a parallel version. I know, well, so GDB, I know people use things other than GDB. You don't have to use GDB. You're actually specifying. Oh yeah. So yeah, the type is CPP DBG and the MIM. Yeah. So I think if maybe you can specify which debugger you want to use via the system, but I haven't tried other debuggers. So yeah.
Is there a question on that?
Yeah, Keith Lindsay, do you want to unmute and ask your question?
Thank you. Thanks for the presentation, Adriana. Maybe I'm a minority here, but
We cannot hear you.
you can't hear me?
Yeah, we can.
Can you type it?
Keith, we don't hear you. So if you want to type it in the chat, I can read it out. Oh, they hear him online. Earlier we heard people from online, but I don't know.
If you want to type out your question, yeah.
I can hear.
Does that do anything?
Oh, try again.
Can you hear me?
Yep.
Still not hear from online. Sorry.
I'm typing.
Keith, are you typing your question?
I think the question is also earlier in the chat. Just go.
So what's it?
He's typing, it says.
Oh, okay.
There you go.
Okay. Question is, what do you get out of syntax highlighting? As a colorblind person, I find it distracting, but maybe there's something there.
Oh.
Well,
Interesting.
I guess, I mean, I know you can pick different color schemes, so I'm sure that they have colorblind friendly color schemes. Go ahead, Sam.
Oh, sorry. Please finish.
But I guess in terms of my use, I guess I feel like it lets me much more easily read code. And then if I'm typing code, I can kind of know if I've made a mistake really quickly, just the different highlighting. Yeah, but in terms of color, I'm almost 100% sure that they have colorblind friendly color schemes for syntax highlighting. So.
All right.
Great.
Okay, thank you so much.
Yeah, could you just
move this side? Stop sharing to not make people nauseous. Okay. So I'll stop presenting here as you present. Okay. Great. So now Sam Rabin is going to give sort of the second half of this, which is a demo of VS Code. Is that right?
Yes.
Okay. That's great.
All right. So apologies if this is hard to see in the back of the room. Found this was the best balance of text size and being able to see everything that I want to actually demonstrate. All right, so I have 3 different sort of demos, some of them more contrived than others, to walk through. A live demo is never recommended, so say a little prayer for me. Got my instructions here on the side on my phone. All right, so immediately you can see this is actually hard to see, and it's not just because of the text size. It's also kind of low contrast, right? It's white background with light blue and orange, which is not really showing up well. And I don't have color blindness. So what I'm going to do is just go ahead and change my theme. And VS Code, so this is just a pure VS Code demo. VS Code has this command palette. On a Mac, it's Command-Shift-P, and you can just type in whatever, and it brings up a whole bunch of actions. So I'm just going to change this to light modern, which has better contrast, and you can see that it actually just previews it for you, which is cool. Okay, so that's a little bit easier to see. Keith, one thing that Adriana mentioned in reply to you about the what is it useful for? I mean, there's a sort of general qualitative, it just feels nicer when I look at it. But she also mentioned it's easy to see when you did something wrong. And here, VS Code recognizes that that import is a special word in Python. This is a Python script. And if I had just import, it would be in black, right? It's also being highlighted by my linter. It's underlined here. But now that it's import, you can see that it's actually the right number. Okay, so I'm using, so Microsoft has a whole bunch of Python related extensions. This is the extensions panel. You can see they're actually installed on in my user folder on Casper. I'm on Casper right now. And you can see that these are out of date. It's because we, in CTSM, we're using Python 3.7. And that, in the past few months, has broken on the latest versions of all these things. So I was able to actually, instead of uninstalling it, there's an option to install another version, which is really cool. And it takes a little while for it to populate sometimes, but then it'll bring up a little window here, and I'm just going to skip that. You get the idea. There it is. So Adriana mentioned the mini map. That's what this is. You can see as I scroll through, it's kind of showing everything that's going on. And what we are seeing here, all these highlights, and they're paralleled here on the very right edge of the scroll bar. These are things that my linter is picking up. So PyLint is saying, here are some things that are wrong, and there are different categories of things that are wrong. They're color-coded, and we'll get into that a little bit. My linter settings, I just want to show off. PyLint for the workspace. So you can see here, I've set some arguments that I want to be passed to PyLint. This RC file, it's pointing to the PyLint RC file that we have set up for CTSM, so it's using our custom rules. It also has disable some stuff that isn't an issue in our version of PyLint that we use officially, but was an issue for VS Code. I'm also saying always use this Python interpreter, this Python executable when you're running the linter, which is important because, like I said, it's 3.7. Right. Great. So we have all these issues with crop-cow module. I'm just gonna, I don't know what that change was, so I'm just gonna revert it. Okay, cool. Whoops. Yeah, so we have this, and sorry, live demo. We're going to scroll down this function, check and trim years. So this is underlined in blue, and it says missing function or method docstring. Well, we have this, or I have installed this extension called auto docstring, which is really useful for this. when you're doing a lot of cleanup, you just type 3 quotation marks, and this command comes up to generate docstring, and automatically populates it with anything that's getting returned, all the inputs, and then you can fill it out yourself. So I'm just going to go ahead and do this and leave all the rest of them blank because we got 15 minutes. All right, so I'm also going to, at the same time, I should commit right now, but just to show off the renaming that Adriana already showed, instead of Y1, which Pylint doesn't like because it doesn't conform to snake case naming. You can just rename it year 1. It does it. All right, so let's go ahead and commit these changes. We can go to the source control pane, and it shows all of this is a full CESM checkout, so it shows all of the repos in it. All we care about is the top level here. So demo commit. Nothing is staged yet. So when we refreshed it, it sees the changes, stage, commit. And it's done. So I didn't have to switch back to the terminal. I didn't have to do anything fancy. I had a little bit of a GUI, which was nice. All right, as I keep scrolling, you can see a little quality of life feature here. See how the name of the function gets stuck to the top there? So I can always see what function I'm in. Pretty neat. And I can click in here. You can also click there, and it shows everything that's defined in the script. And it'll show also where new variables are defined, etc. Right, so I'm just continuing to scroll through here, and we reach a red stop is not defined. So that's not Python code. I don't know who did this, but let's go ahead and try and fix it. So this is where I'm going to demonstrate searching with regex. And I just need, I'm just going to go ahead and copy my regex there. So we go to the search pane, and we have this. This basically means search with regex, use regular expression. And we can paste it in there, and it highlights all the occurrences. You can see, you can click around. Right, so that's all bad. We don't want that. I remember the code before, and these were all runtime errors. So we can do a pretty simple search and replace. So we expand that little caret, and now we see replace there. And so because we defined these groups in our regex, there and there, we're able to use those in the replacement. And just like before, or just like Adriana showed with the renaming, we can preview if we want to. And it's hard to see. I know it's just, yeah, it's doing it inline. So we're replacing these 2 lines and with the raise runtime. So let's just go ahead and do it. Yes. Cool. So we can go ahead and save. Every time you save, Pylint reruns, and that can take a long time for a very large file, but not supposed to have long modules anyway. Right, so that was weird. I don't know who did that. Let's go ahead and undo it and just figure out who the culprit for that might be. So we're going to use the GitLens extension, GitLens inspect. And so here you see the line history information. Sam Raven. Thought I defeated that guy. His dastardly deeds knows no bounds. We're gonna have to repair the veil between the evil universe and R1, but for now, let's just go ahead and fix this code. All right. So what else did he do? And you can look here. Golly, this looks bad. Okay, let me go ahead and close that and expand this. Right. You can expand the author name. No, we can't. All right, Sam Raven. So he's done at least those three. We'll just do a quick search for author evil. All right, only 3 results found. And again, just like before, you can search with regex if you want to. So it's just those 3 results found. Good. So we can, if we want to, we can just go ahead and right-click here, this last known good commit, and we can say reset current branch to commit, and it'll give us the option of regular, soft, or hard. Very nice little feature set there. So GitLens is really cool, and I actually only started figuring out how cool it was when I was putting together this demo. Right, so instead of fixing all that, I'm going to let the Avengers deal with Sam Regan, and I'm just going to demonstrate a couple of silly things. So multi-cursor support, you can do this in Vim with Control-V, move around with your arrows, Control, hold down Shift, press I. But you can also do it in VS Code in a much easier way. On a Mac, I'm holding Option. You can see the cursors at the end of this first stop, and I can hold Option, and now I have 2 cursors. I could even put it in a different place if I wanted to, right? So not the same place on the line, which you can't do with that Vim method I just described. And I can just add whatever I want here. And I also downloaded this extension called, I actually didn't download it on Casper, so I'll show that later. So that's pretty cool too. Right, so that's that one. Restructured text files. Who here has to deal with restructured text files? Yeah, this is what we use for our documentation, and they're a huge pain in the butt. It's a really weird syntax. You're always switching between your editor and a browser or something like that. Well, actually, you can just do it all in VS Code. I'm going to turn off the mini map because that's just taking up space. You don't need the search pane anymore. So first of all, we're seeing these are very long lines. I like having long lines in doc files, but it makes it hard to work with. So I've set up a text keyboard shortcut. Pretty much anything you can do in VS Code, you can set up a keyboard shortcut for. So I can wrap text with Command-Shift-R. It's very nice. And it's wrapping it to the window width, but you could also set it to wrap it this guide bar that Adriana mentioned. All right, so what we're doing here is we're looking at a piece of documentation from CTSM having to do with crops, and we can open a preview to the side. And so now we're previewing the docs live. And we have a really nice feature, which is scroll sync. So you're always in more or less the same place on the preview and the actual code. So I'm scrolling, I'm just looking through. All right, so I've noticed something that I would like to change. There's this H, which is a variable. Everything else that's a variable in this paragraph is in the sort of mathematical font, but H is just italicized. So let's go ahead and fix that. It doesn't sync perfectly, especially when the text is this large. So I'm just going to search for it so I know. Right, so that's what it looks like. But I want to make sure that this is fixed everywhere. So I'm going to open our search pane again. And it's searching for H everywhere. And you can see that it's highlighted 22 results in 9 different files. Okay, so this one, yeah, we're only interested in lowercase h, so we can set that. But we're still finding some results in the Fortran files. So what we can do is stand here and say exclude. But now we're finding it in a Python file, and there's this text file that also got included. And so we're just going to say .rst. It turns out it's just this one file that had the issue.
14.
Okay. And last one, just going to illustrate interactive Python. So I'm a big MATLAB boy, or at least I used to be, and I wanted a way to work with Python that works sort of like MATLAB. MATLAB has this concept of cells. Actually, Python in VS Code has support for this. So I can delineate a cell with this, and I just hit Command Enter, and it runs it, except we don't have the right environment loaded. So I could select an interpreter like this, just from the command palette. You can also do it from here. Python is aware of all your different environments that you have. And I'm just going to switch to this one. I guess I can't switch to it from there, so I'll just switch to it here. So it's switching. And I close this, close that, and rerun. So now it's working. I'm going to run this setup cell, and I'm going to make the figures. There's an error. Okay, that looks like it's not the right name of the function that I meant to call. It's in a different document, right? And so I can just click on the line that has the error, and it opens up that document for me and puts the cursor there. I could also have run it in debug mode. You see the little bug there? Running in debug mode. It's going, and then it highlighted the correct line. And like before, like Adriana showed, we have access to everything that's loaded in the whole call stack. Okay, so I know what the problem is. I just need to change this. And I can rerun this, seeing the update, and that's because I need to say import lib reload utils. Now it works. And you can also do all this, instead of this weird hybrid of cell sort of format, you can actually just write notebooks in there as well.
Cool.
So yeah, that's it. Thanks.
Well done on that live demo that actually. There's some conversation in the chat that I'll just read out here first. Chris Fisher asked, how well does VS Code work over a slow network connection? There was a few answers in the chat about it actually working better potentially than a terminal because it buffers the text that's being sent. And also Eric, Alper pointed that out. Eric pointed out that a lot of times you're going to just work locally. I don't know if either of you have anything you want to add.
I've never had issues with, working remotely. So
Yeah.
in terms of the connection, it's great.
Yeah, sometimes it kind of stalls out on the initial connection.
Yeah.
You might experience this.
Right.
Did you ever figure out a solution to that, or?
Yeah, there's like a VS Code server directory in your home directory on the remote machine. And then if you remove it and let VS Code recreate it.
Makes sense.
And I will, in terms of the remote SSH stuff, just because I got into trouble, not really, but so when you open up a workspace in VS Code, it's like the workspace on the when you're navigating. And so I think one time my workspace was like my entire work directory on at the time Cheyenne. And when you do that, like the linter is like constantly like going through all your files. And so I apparently was using like a lot of memory. And so I got all these like emails like, you're violating. So just open up a single directory that you want to work in, not your entire work directory. But
I'll maybe just continue with some online questions before we go to the room. Keith Lindsay asks, I've attempted to spin up on using VS Code to edit remote files via SSH using VS Code extensions. It seems like some extensions get installed on my local machine and some get installed on the remote machine, like Fortran linters. I'm rather confused by this. Could VS Code gurus clarify?
I think it should just be a matter of if you currently have a VS Code window open. So individual VS Code windows are connected via SSH. So this one says SSH Casper, this one doesn't, right? So this is a local one. I actually ran into this, right? I have a different set of extensions installed on Casper, and that's because when you want to add an extension like sequential text, which is the one that sequential number that I forgot to show you, there's a button that says install in SSH Casper.
yeah, so you usually have to reinstall you can install your extensions. And I mean, I actually find that nice. Like, so the worst case, like workspace is kind of different, depending on where you are. And you can even set workspace specific settings too. So like I have different settings for like CTSM than I would for another model that I want to work with. Like, so say like in CTSM, we do 3 spaces, per line. You want to like jump into like a loop, but with other source code, they say, no, it's 4 spaces. And so you can set those up specifically.
Yeah, so here you can see there are 3 tabs in the settings menu. There's user, so that's whenever I am using VS Code, and that actually syncs with your like Microsoft account or whatever. I can set settings whenever I'm connected to Casper, and I can also set settings specifically for individual workspaces. And the order of precedence goes most important, second, third.
Let's take one final one.
You had one on the
For me?
Yep.
Okay. So I was just curious again about SSH connections, what gets installed locally on your laptop versus what gets installed on your remote platform, and what kind of permissions does it need to get installed there?
On the remote platform, and I think locally as well, it just gets installed in your user folder.
Okay.
So you don't need any special permissions unless your user folder is locked down for
just internet access.
Just internet access, exactly.
Okay.
And so yeah, it's worked with Derecho, Izumi, Casper are the ones that I've tried it with. It's all
All right, Sam, I think we're gonna keep moving. I think the next presentation is remote, right?
Yeah, so we now have one final VS Code related presentation before lunch from Supreet.
Should we figure out how to hear in the room before we start?
Yeah. Okay, good point. Yes.
Hi, everyone. Can you hear me?
Speak to us.
Okay, great.
Is
Hi,
he
everyone.
speaking?
My name is Supreet Suresh.
We
Can
won't know
can you hear
until
me?
we hear him, I guess.
Can anyone?
Maybe we could turn one laptop speaker.
He's speaking, we can't hear a thing.
Okay, yeah, I could just turn on my
Yeah, and put it in the middle. Yeah.
well then
I think if you
let me use this one.
If you turn on your speakers, then you create feedback for people that can hear. Unless we mute in the
Can you
room.
try it now? Okay, can you hear me now?
Good. Yay. Good job.
Okay, great.
How many software engineers does it take to turn on a speaker?
Okay, I can get started if everything is okay.
Yep. Yeah, we're good. Thank you.
Hi everyone, my name is Supreet Suresh. I'm a software engineer and CESL PhD ASAP group. Today I'm going to present a little bit about GitHub Copilot. So you guys heard the presentations about VS Code. Now I'm going to add a little bit on top of it, which is called the GitHub Copilot, which takes this, whatever Adriana and Sam mentioned, to a different level, one level up, I should say. Okay, so what is GitHub Copilot? It's a AI-based program running inside from GitHub. It's based on a large language model, LLMs. So there are multiple AI programming assistants available, but today we're going to concentrate on the Copilot. So one thing to know about is it boosts productivity. It is not, few things to know about is like it boosts productivity. It is not a compiler. So how it works is like it understands the pattern from millions of publicly available repositories online, which is being used as a training data. It understands the context of your code and try to predict what's next. You can choose to accept that solution, and from the list of solutions you can choose to accept, or you can ask the question in a slightly different way. So unlike the ChatGPT or any other AI, the Copilot only answers questions about your coding, general questions about your coding. So, and also some programming languages are better supported right now than others. For example, Python or JavaScript, which is widely used, has better support compared to Fortran or, some old ancient language. One thing I want to caution everyone is we have to trust but verify. You have to check the solution and ask the Copilot again if you find any errors in it, saying that this is the error that I got, and that the Copilot can correct itself and give you a more relevant information to fix your error or to use a different library or write the code in a different way. So this auto-generated codes can introduce bugs, so you have to be careful and you have to test it really well. Okay, so now that we have a basic general idea about the Copilot, here are some steps to enable it. You have to log into your GitHub account, go to your profile, and there is an option called your Copilot. From that, you can enable it. I've been using the license from NCAR provided by NCAR, which gets billed to our account. But you can request an individual account as well by providing your credit card details, and you get like 30 days free trial to try it out. So once you have enabled your GitHub Copilot in your GitHub account, you have to add an extension in your Visual Studio Code called GitHub Copilot, and you can sign in with your account, and it gets added to your account, and you can start using it. So, once it's installed and enabled, you get this chat box on the left-hand side of your extension that says that you can start asking questions. So now that we have enabled and installed, how do we actually invoke the Copilot inside the VS Code? There are multiple ways to do it. So first one is obviously that you have installed that extension. You have the chat box. You can start asking the question that I showed in the previous slide. If you're on Mac, then you can press, you can open any file and press Command I or Control I for Windows, and you can start asking question. Or you can select a part of code and just right click. There's a Copilot option available to you, and you can start using those. Or you can just start typing. It will just predict what's next. You can choose to accept by pressing Tab, or you can start typing more and get a different solution. One small point is there's on the right-hand side or bottom of your Visual Studio Code, there's a GitHub Copilot icon where you can do adjust some settings, as well as you can check the status and access documentation related to Copilot. Okay. So what's the main difference between, you can just use ChatGPT or Gemini or any of the product side. I think the main difference between the Copilot, using Copilot from Visual Studio and any other AI is the GitHub Copilot is able to take your code or what you're trying to do as context. So a lot of these AI, they are limited in the token size, input token size. So it's not able to take the whole context into picture. But when you use it inside the Visual Studio, it is able to take that context of what you're trying to do. So the next question we want to understand is, how do we give Copilot that context? There are several ways. You can open files, multiple files, or a single file that you want the Copilot to consider as a context. It looks at the top level comments in your code. For example, if you have a Fortran module, you write you can, if you have some comments at the top saying that this module has these many functions and it does ABC, then it is able to take that as a context. It looks through your use statements or the import module or the include statements in your code and take that as a context as well. Additionally, like you can take if you name your variable properly, like instead of something like tempex, if you properly name this, a variable with some scientific context, like it is able to consider that as a context and identify and specific comments about your code, saying that this is an implementation of this particular equation. It is able to consider that as a context, and even if you just give a sample code to it, it is able to take that as a context. All of these things are managed by two kind of key variables, as I see it, that is at workspace and at terminal. So workspace is nothing but the files that you have opened, as well as in the GitHub, when you open the Explorer, you can see the set of files that is considered as your workspace, and of course the terminal. Okay. So now that we have understood a little bit about context, I want to do a quick demo on what are some of the things that I've been trying and I've been using it for a while. I've categorized it into 6 things. I'm gonna get through them one by one. Let me switch. Okay, can you guys see my Visual Studio Code, VS Code window?
Yes.
Okay, great. Okay, I don't have the syntax highlighter enabled for this, but I'm just gonna go through that. Okay, the first one is you can write any basic code really fast compared to what you would write by hand. For that, one example I can give is, for example, I have this impasse code that I'm working on, and I'm working on porting this particular kernel onto the GPU, but I have some issues in the validation. So I want to extract this variable and then take a look at the data which inside this variable. So normal way would be like we collect the data from all the processes and write it into a file, and then we can take a look at the files, or you can run a debugger as well. But if I have to include those statements to write it into a file, I have to manually code. Instead, I can ask the Copilot on the left-hand side. You can see. Okay, now here I'm asking the question. I want to write a Fortran subroutine to gather w_10 variable from all the MPI process and write it to a file. Okay, now you can see the GitHub Copilot is able to consider my file that I have opened as a reference. I'm just gonna show that once it gets printed, everything gets printed. So I can see it used this particular file and some line in here in this file as a reference, and it gave me a subroutine that I can just copy or just push to the right, and it just collects all the information from all the MPI process, and it opens a file and write it into a file. But what if I want to write it into a netcdf file? I can just say write it to a netcdf file with parallel IO. So it is able to understand the context that I'm trying to write the W10. So it gave me a modified program or a subroutine that I can include to write using PIO instead of into a NetCDF file instead of a normal text file. So yeah, you can write some of this basic code that you probably take, for me at least, it would take, for me, if I had to manually write, it would take me 30 or 40 minutes to write all these things and get it right. I can just start from here as a basic point and change it and figure out like what comes next. Okay, I'm gonna run through a little faster now because I'm a little short on time. So the second thing is it helps you remember some of the stuff that you have forgotten. So you can, for example, I always have trouble remembering the PBS, all the commands in the PBS. So I can just ask, write a PBS script with GPU support to launch a MPI application.
Hi, Sapreeth. I know you're keeping track of your own time, but just want to tell you we are at 13.5 minutes.
Yeah, sorry. Okay, so it can help you remember some of the stuff that you've forgotten and make it faster. So, okay, I have 3 more examples that I'm going to get through if that is okay. So the next one is refactoring and rewriting the code. So like last week, we were in a hackathon where we took a C program and wanted to rewrite it with GD4Py. First step was to convert it to NumPy. So we can just select the part of the code that is written in C, and you can ask command I, rewrite this in Python NumPy. So it's gonna go through the whole code probably right now, but it can actually rewrite it in Python pretty easily. So some of this refactoring and rewriting is kind of really easy with the Copilot. So a couple of things. It can help you understand, explain, and understand an unfamiliar code. So you can just select a code and ask the Copilot to explain this. So if you have trouble understanding a particular piece of code, it can help you break down pretty easily, so you can able to understand it better. And also, it can actually add documentation to your code. You can just select this part of the code and say, I'm going to use a different method now. If I right-click Copilot, it can generate documentation for your code. So it's just a basic documentation, but you can improve on top of it. 2 more things. One is it can help you understand your error messages. So if I open a terminal, if I get some error message, either here in the terminal or in the log file, I can select that error message and ask, instead of doc here, I can just ask, explain that error message or fix that error message. It will try to fix that error message for you, or it will give you options that you can try. So it could give you a list of options that you can try to fix that problem. Another great thing, or another really interesting thing here is we can actually create unit test for your code pretty easily with Copilot. So I can just say create unit tests for this code. So it can generate unit tests for you, so you don't have to write it from scratch. You can just take this and improve on top of it. I can just ask in Python if you want Python testing. For some reason it took I can just select and ask again to write it in Python. Okay, so those are some of the things that I wanted to demonstrate for you guys. This is just a summary slide. Yeah, any questions?
Time for a couple quick questions.
I'll ask a question. Thanks a lot for presenting this. And this is, yeah, I hadn't seen this demoed like this before, so thanks. How well do you find that it works, especially for Fortran code? How accurate do you find its suggestions are?
I find it really accurate, but again, it's the base version it gives. You can always make edit and change it to what's suitable. But although I think asking question in a different way always help me. Like if you don't find a acceptable solution, for example, if Copilot generates some something that you don't like, you can actually load the suggestions, like see you got multiple solutions and you can actually accept as a solution. It's just giving me 3, but it can give up to 10 suggestions that you can choose to accept or deny. But for my cases, at least, it's been working really good, and it is mostly accurate, except for a few minor bugs that we can readily identify.
Does it remember corrections that you make? For example, I noticed in the PIO example that you gave, it incorrectly limited some of the calls to processor 0. If you tell it, you know, like the PIO defdim is a global or a collective operation. If you tell it that once, will it remember for later?
Yes, it does. And it is able to correct and give you a modified code as well. If you have an issue, let's say this function is wrong, or add another argument, you can just specify like add another argument to this particular function or subroutine call. It will do so.
Okay, so this is magic. BI does not do this. So I'm getting more and more sold after these 3 presentations. One feature that I'm curious if anybody knows about with using this tool is if it goes one step further and helps with the code management part. Like, does it know, like, does it have GitHub docs in its training data as well, so that I could point somebody that asks me every time, like, how do I get my code into the remote repository? And it knows the commands that you might need to do to make that happen because it can see your workspace.
Yeah, you can ask any question. So
Would it
what did
be
you want to
able to
ask?
say you need to like commit and then push based on the fact that you have changes locally?
How do you do a git push from VS Code?
Nice. Okay. Oh, now I want to make everybody use this.
Great, thank you.
These talks before lunch because I figured they'd be really interesting conversation too. So, yeah.
Sorry?
Yeah, so let's break for lunch, and I just want to remind everyone, so what time are we coming back? I think 1 o'clock?
Yes.
1 o'clock. And just for those who have joined since the beginning, I just want to remind people that at the end of the day, we will, some of us will be going to Under the Sun. And actually, can I get a quick show of hands? No commitment needed, but how many people think they're likely to come to Under the Sun? Okay, and people remote, you are very welcome to join us as well if it's not too long of a commute. We'd love to see you at Under the Sun, even if you cannot come to the meeting in person. All right, great. We'll see you back well, hopefully we'll see you over lunch and then we'll back at lunch.
It's a good point. I didn't think about local people picking up this 50 far away.
Yeah.
But
just fly in for the together.
Are we safe to leave our stuff in this room for lunch?
It is
I
open.
mean, I think it's safe, but I don't want to. I mean, it is. It's kind of a public.
It's not behind closed.
Yeah, it's a kind of public area.
Yeah.
Okay.
Yeah.
Are you taking yours with you?
Theoretically.
Oh,
Guys, I'm from São Paulo.
A little tired on today morning.
It's what?
But
From São Paulo.
introduce myself.
Oh,
I've been in now with
How I know how to do it.
process coupling.
I can leave my.
Yeah, it's probably
Unfortunately.
Yeah.
Years we were together on these things.
oh, it's a good place to put my water bottle while I tackle
Get a
too many
schedule.
lunch.
Not do that as much. But a particular problem we're trying to solve is multi-rate methods in the model. Which means instead of doing just sequential splitting or sequential splitting.
I've been a
with,
long time
like,
Emacs user. I'm
stuff,
trying to switch over to VS
trying
Code, but
to
I
split into
there actually are like
And
plugins for
so
Vim and Emacs for GitHub
processes in the
Copilot
physics
as well, but it just takes
better
more.
than
Part of it for me is
call
like
and kind of
all these modern things are like, I could spend a few hours trying to get this set up, or I could just like.
So
use the-
one of the things that's coming out of this is there's more and more interest. If you guys, we're gonna have like a boot camp, like a 4-hour hands-on. Here's how you get going. Let's try it with your code.
Models that
And
have
tap into these experts who know like it.
I also want to get the RDH PCS
subdivisions.
folks on
It's all
board
manual,
to give us some hints.
more or less. Like almost all
This
processes.
for using it over FSH on
Until very
government
recently.
systems.
Right.
New
Um,
tools and,
I did the same thing with
but,
Python
yeah.
notebooks like
Sure. You had
several years ago, and it's kind of
If you
become the
need
regular thing
anybody
now.
else. Right,
So
okay.
That's,
instead of like our group.
I guess, VS Code very light, right? It's closer than.
I mean, this stuff is pretty magic. I was thinking VS is like voodoo stuff, which is sort of like this. Pretty awesome.
Think about the dynamic.
We got one or two more, you said.
Or the cross.
Yeah.
Absolutely.
Coupling eventually.
Yeah, so there is some.
Yeah. Well, let's see, so Sam got the PowerPoint. Working actually. So that'll work, and then the PDFs.
Okay, let's start the radiation somewhere. Let it put its tendencies and stuff like that. CPU.
Yeah,
And then final CPU.
yeah.
Something like that.
So yeah, that kind of parallelism is useful. I guess the other thing is actually having multiple calls. So if you wanted to implement something like string splitting, you might have, say, like random example, like 2 microphysics calls to the same parameterization, but twice in the time step, and then have something else interleaved in between. Or kind of more complicated structures like that.
Okay. Yeah.
So I'm a little curious, like how reentrant a lot of, or assuming that the underlying parameterization is defined to be called every arbitrary number of times, if CPP can actually handle
Yeah, well.
calling the same
yeah.
code at like different points in the time.
Absolutely, yeah.
Yeah. Okay.
Fine. In this case, maybe either have, what, if it's exactly the same set of schemes you're calling, you can have the same group, you put in a separate group, and you call that group here, and you call that group there.
Yeah.
Sure.
Oh, wait, I think my speaker muted. Hi again.
Hi. That's the second time.
Yeah, it's fine. I'll probably want to sneak away to lunch sometime soon, but should be good to chat for a little bit at least. I was trying to put together some document materials of things. I was going to I'm not necessarily sure what you want to focus on in terms of like, what do you think would be good to write about in terms of the event? Like, there were 9 teams, I believe. I want to double check. 1, 2, 3, 4, 5, 6, 7. Yeah, 9 teams. I just shared with you a little Google Drive folder of like their final presentations for each of them, which gives a good overview of their like discussions. And were you able to make any of the presentation sessions during the last week?
Yeah, I made one. I didn't get, and then on Thursday I attended for like a half hour at the end.
Okay.
To see it. But I'm not sure I understood what was going on though, because it was very technical and I just wasn't sure what.
Yeah, like,
You know what they were talking about.
no, it's fine. I mean, like yeah, most of it was technical, and I think like it's kind of hard to suss out maybe what was like the important pieces in terms of like what each team's presenting on. And I think like what I would probably focus on and how you might choose to elaborate or not on it is just like the performance improvements each of the teams got. That's usually what we tend to focus on, which because like that can in the sense of defining performance improvement, you know, say like they implement some new code software solution and it allows the code to run like 10x
Yeah.
Yeah, the actual triple bypass does this big pass over, starting in like Evergreen, and then goes down into Georgetown.
Oh,
That's
actually,
actually the biggest.
Yeah, I know he's doing the Camp SEMA
I
side,
forgot
but.
that.
Oh,
It's really good too.
Plus, like I said,
Somewhat.
I don't know anything.
Yeah.
So triple bypass, three passes.
Three passes, yeah.
Yeah.
Seems like a iffy.
I'm waiting for that one.
Yeah, I was telling that to like my parents. I'm like, I signed up for the double bypass, and they're like, "What?"
You signed up for it.
You volunteer for that?
And I'm like, "What have you not been telling us?" I was like, "No, it's a bike ride." But yeah, so they have a big one, and then they have Loveland, which is huge anyway. And then Avila is actually the least of the three. So at least they kind of line it up. If you get more tired, there's less elevation. And then, yeah, like the last 25 miles are all downhill. So that's a bonus.
But you really had to earn that last 25 miles.
All right, we will get restarted here. Welcome back. Everyone had a good lunch. We're going to be shifting gears a little bit this afternoon and learning about some work in the post-processing and diagnostic space. And to start off, we have a joint presentation from Tegan King and Mike Levy on the CESM Unified Post-Processing and Diagnostic Cupid effort. So excited to hear the updates on this. Oh, we're not sharing here, right? Yeah.
Hi, Mike.
The high mom sign on TV. Hey, well, hi everyone. I'm Mike. This is Tegan. We're going to talk to you about the CSM diagnostic, which is a project that has been spun out of ESDS. And I'm glad to see familiar faces in here because our next slide is talking about what ESDS is. And a lot of the CGD folks have seen this slide somewhere between 2 and 5 times. So it'll be new for newcomers. So Earth System Data Science, or ESDS, is an NCAR collaboration that kind of started from the ground up. That some scientists in CGP and CISL were talking about how to they can improve their analysis of Earth System output. And at this point, we've grown into being run by a committee with representation from a bunch of different LCPOs in NCAR. Keegan and I are 2 of the representatives from CGD. We started in the fall, and a little bit of history because we have so much time for these slides. So Katie Dagan and Deepak Sharian have been the CGD reps for a while, and Deepak left, and he's been replaced by the 2 of us. And Katie is wrapping up her term for, I think she has another month, being the 3rd on the committee. Anyway, the big focus for ESDS has been this push to pipeline. Like NCL has officially been sunsetted. What do we do to analyze model output? Well, we've also been focusing a lot on community building, just kind of creating a culture of open science and development and sharing ideas and code. So I call this my NASCAR slide. There's a lot of logos. So big issue is that CSM users, besides NCL being sunset and not being developed, like we're hitting the limits of what NCL could do. It's a serial code. If you try to analyze 30-degree ocean output, it's going to take forever, and then eventually you're going to crash the machine that you're running the code on. And so there's this big advantage making sure that everybody replaced NCL with the same product. And ESDS has helped find a solution, at least here at NCAR, where we're getting into this Pangeo code. NumPy, X-ray, matplotlib, yeah. But at this point, we still have a bunch of independent efforts for analyzing the CSM output. The Atmosphere Working Group has spun up ADF, which is either the AMWG diagnostic framework or the Atmosphere diagnostic framework, depending on who you ask. The Ocean section had this ND Squid. I know the MD stands for notebook. I'm not sure about the squid part. And then there are a lot of people just writing one-off notebooks. And so it's great for quick and dirty analysis, but if we want a product that everybody can use. It would be great if we're all working in the same framework. And so that was where Cupid came from. Most of these names are CGD folks. These are the people that have been working on Cupid for the past 4 months or so. So Tegan and I are here talking about it, but it's not just our work, it's a big effort. So the project vision for Cupid, the collaborative effort that's going to unify all of the CSM component diagnostics, and the output will provide Python code that runs in an easy to generate kind of environment and can be launched either through the SEAM workflow or just independently from the command line. And we want to be able to provide diagnostics for single runs or ensembles, and just from a single component or from a local run. And we want to be able to call post-processing tools that other people have developed. So there should be hooks for plugging in other code into the Cupid framework. We want to provide an API of the same thing twice. And then we need to provide ongoing support and maintenance for moving forward. We don't just want to dump Cupid on people and then be like, all right, we're off to do other stuff. So this was a timeline that we put together in the fall when we were trying to sell CGD folks on the Cupid effort. And so we've highlighted in the top left kind of 3 steps that we've already taken. So we got a group of people together. That was a couple slides ago. We really kicked off the project at the beginning of December. And then I looked at the commit logs, and by January 9th, we had combined the atmosphere and the ocean projects into a single Cupid repository. And on the bottom, you can see that we're trying to do this in line with the CSM development timeline. This is really something that we hope can grow along with the next release of CSM. And this is, at this point, probably a pretty standard method for organizing projects, but everything is in a public repo on GitHub. It's in the NCAR organization. We're having users work the repo and they make branches and then submit pull requests back. We're using GitHub IO to provide documentation, and we're trying to make copious use of the issues board for bug tracking and the project board for kind of organizing milestones and trying to get everything done. At this point, I'll hand it over.
All right, so I'll share a bit more about some of the details of Cupid and the current status of Cupid. So we currently have a single command line that we can use to produce basic diagnostics for the atmosphere, ocean, land, and sea ice components. As you can see here at the very top of the screen, we say Cupid run and then add a config.yaml file. That's a user editable file that controls what particular notebooks are run and any parameters that are passed to those notebooks. Cupid Run uses Plumer, which wraps paper mills in order to run notebooks and pass any parameters from the config files to those notebooks. So it's a pretty streamlined way of running diagnostics for all of those different components. So each component is run sequentially as of right now. The runtime is somewhat variable, and that's somewhat due to the resources being shared across different users. We did some tests using Q Interactive and using 14 different nodes for these tests here. So we wanted to try both using Dask and not using Dask in our notebooks and see how we sped up the time to process the notebooks. So using Dask local cluster for parallelization, the Ocean notebook took 4 minutes and 23 seconds. And then without Dask, it took about 10 minutes. So we have sped up that process a decent amount. And there's still some variability. The best runtime was 3 minutes. And the CIS notebook started out taking about 25 minutes to run. And then with Dask, it takes about 13.5 minutes. So this is something we're kind of keeping an eye on and working on making sure that it is feasible to run this efficiently for people to use it. And so we also have 2 environments set up to be able to run all of Cupid. So we have the Cupid run is executable in the Cupid dev environment. And so we're hoping to have the Cupid dev environment be added to NPL, hopefully with the help of Sizzle. And then we also can run all of our notebooks in the Cupid analysis environment. So we really wanted to have a constant Cupid analysis environment where all of the diagnostics for the different components can be run with that one environment. That environment is built on the Pangeo stack and also uses GeoCap. And then I also wanted to note we've been working on migrating functions into GeoCat, for instance, from the atmospheric diagnostics framework. ADF, we've been pulling out functions that have to do with plotting or that sort of thing that can be used for other component diagnostics. And we're trying to get those to go into GeoCat so that they can be more robustly shared across components. We also have step-by-step instructions for adding new diagnostics to this framework. So you can check out our github.io page if you want to look at those. We really wanted to make it very simple for anyone to add a notebook to Cupid without having to really get into the weeds of Cupid. And so this is mostly just like, how do I set up my notebook so that I have parameters at the top of the notebook and use the Cupid analysis environment. Everything runs smoothly when we then like merge the notebook into Cupid. So we're trying to make this as streamlined as possible for people to contribute to, and then also be able to run everything kind of simultaneously. So currently our Cupid output has kind of two options. You can either go and look at the particular notebooks that are run, or you can use this Cupid build command to actually create a Jupyter book with all of the plots from the notebooks. And so it's really nifty. On the left side panel of the web page, you can click through the different components and the notebooks that are run within those different components to check out some of the diagnostic plots that are created. So here we have some plots of sea ice concentration that were created in the sea ice notebook. And so everything is kind of in one cohesive location after running the Cupid build command. We're probably going to change that function name, but the gist of it will still be there. A couple of directions that we are headed is that we want to have a Conda kernel available on Casper and Duratio. We're also hoping to launch diagnostics directly from the scene workflow, as Mike mentioned earlier. We really want this to be like a smooth transition after running a CSM case to also run the diagnostics. And then we're hoping to continue to port NCL-based code to Python during this process as well. So overall, this project is really fitting into the ESDS cross-lab initiative at NCAR, but it's specifically focused on CSM3 diagnostics and moving forward from that point. We're still in the early stages of development, as you can tell, but we're really excited to be progressing this forward and just wanted to share with you all sort of where we're at right now. So that's about it. If we have time for questions too.
Yeah, thanks a lot for that. And we do have time for questions.
I'm really excited about this. I'm just curious, what is on your wish list that you don't know that you'll get to yet? Like, what's ahead? Yeah.
So I mean, I think like like all these examples that we've shown, like these notebook, do not know. So like we have 4 notebooks in the left sidebar, like one from the atmosphere, one from the land, one from the ice, one from the ocean. And those are all just really like toy notebooks. And so getting more direction on like what the output should actually look like. Like should we be focusing on what comes out of the CSM post-processing package? Should we be building something new? Like what's actually needed when we create this Jupyter book? Because I think the framework is coming along.
Great. Thank you.
I am mostly working with NCS still, so what's the best way? Because I have a bunch of NCS scripts that do lots of things for me. So it's easy for me to go those NCS scripts and then get the pieces and then create another one. So what's the best way to move to Python for me as a regular user?
So there's an NCAR effort in CESM called GeoCat that's really working on Pythonizing NCL. And like it started with a hackathon where people just like picked random examples from the ncl.ucar.edu page and converted them to Python and made them available. And so
at the end of the day, you have to go those NCS scripts and then you have to port them to Python, right? So it will be too much work for me.
Yeah, so I mean, if you talk to GeoCat, like they're tasked with doing that, and
So
I
is
think
that
they're begging people to tell them.
So the next talk is best.
Yes.
Okay.
Who's next?
Yes, go back to the notebooks, kind of like initiative there for that project. Are there any plans to engage with the AGU Notebooks Now project in terms of like facilitating like publications, utilizing notebooks to showcase this in a more broad photo sense?
I guess I hadn't personally been aware of that project, and maybe it would be good to get more information about.
Yeah.
So just more clarity on the NCL issue, because you did say, you did on the slide, it says, converting NCL functions to Python. But from what you just said, it sounds like GeoCat is also doing that. So are there some things you're doing and some things they're doing?
GeoCat has folks involved in the Cupid project. So like our Cupid analysis environment will bring in the GeoCat.
Oh, okay. Okay, so they're part of it. The GeoCat people are doing the NCL translation. And so the two of you aren't for like this, the CGM side. Oh, okay.
And I think this is also
Okay,
a kind of nice example project to figure out what actually is really useful to bring into GeoCat. Like, what are some of the functions that multiple people want to use that could be, more robustly defined and then can be brought back into diagnostics for multiple components. So I think it's kind of a like case study of what's useful to bring into GeoCat.
Yeah, that makes total sense. Thank you. Yeah.
Dave, did you have?
Yeah. So we've talked about this before, and you probably haven't quite gotten around this, but just asking is, if you wanted to call an entire different package, like there's ILAM, land model benchmarking, there's ESM val tool, there's NOAA, all.x task force. I think the design, you're trying to make it amenable to that, but have you thought about that, how that would work at all? So you can imagine on this page, it would end up as another, whatever bullet on there, or it might be under one of those bullets is that, if you asked it to call ILAM, it would call ILAM, and then ILAM would do all its thing and produce a web page, and you would just link to it, but it would make it so that the user didn't have to know everything about ILAM or ESM val tool or all these other things.
Yeah, so I don't think ILAM is in the Cupid analysis environment now. Like we could try to put it in and see if it conflicts with anything, and if it doesn't conflict, like it's just there. And then when you run these, I think the Cupid base code can support running different notebooks in different environments, and so I don't think we want that in kind of like the out of the box configuration, but I don't think it would be hard to show WAN developers like, oh, if you just add this block to the YAML code, as long as you have an environment where IWAM is available, it can be there. I think I guess it comes down to like, is the IWAM diagnostic something that we're going to want out of every run, or is it something that the WAN developers are going to look for specifically that other users of CSM might not need to look at?
Well, I do feel like we would want, in particular, ILAM would be one example where we do want it, but I think just in general, I feel like across the CSM project, I'm concerned that, the way it's working right now is that, person X knows how to run ESM val tool, person Y knows how to run the NOAA diagnostics task force, person Y knows how to run ILAM, and ideally anybody could say, I want to run the ILAM diagnostics, and if it's all set up in here that you would just have to flip the switch or whatever it is out of your YAML file, it would be a really nice benefit, I think, to more people accessing these more advanced diagnostics that have already been built, right? That's the thing, is that we're going to build something that's going to be really useful for us because we do it all the time, but people have put in, especially comparing to ops, really clever diagnostics that would be nice to really fold in. So one suggestion would be is to take one of these packages, whichever one, I don't know which, and just see, what it would take to ingest it and make it possible to make sure that the framework is amenable to that. Sounds like it is, but it's all the devil's in the details, right?
Yeah.
No, nothing mine.
All right. Well, thanks again. The work that you've done putting this portfolio together. Next is remote talk. Let me stop. Sorry. Stop sharing
Who's going to
here.
present the CESM?
Yes, the next talk is from, I hope I get the pronunciation of your name right, Anissa Zacharias. Maybe you can pronounce your name for me so I know how to say it in the future. But continuing in the same vein of post-processing diagnostics and building off of Ufuk's great leading question, we'll be hearing about how implementing legacy MCL routines in the Python ecosystem. So great, we can see your slides.
Great. Yeah, can everybody hear me?
Yes.
Okay, great. And you were close. It's Anissa Zacharias. Very close. So, right. Hi, folks. My name is Anissa, and I'm going to be talking to y'all about writing new old code and GeoCat's process of implementing legacy NCL routines in the Python ecosystem. Also, all you guys that had questions last time about NCL routines, I would love to hear from you guys or even just like get an email. I am so interested. But yeah. So to understand the GeoCat team, first we need to discuss the Pivot to Python initiative. The motivation and execution of the Pivot to Python started in May 2018 when the NCL team developed a survey asking NCL users about critical NCL functions, their experiences with Python, including Python support, and just like training they would need, and their opinions on moving to an open development model. In August of 2018, an NCL advisory panel found that transitioning NCL to Python was necessary to maintain NCL's utility and relevance as a data analysis and visualization tool. In 2019, a roadmap for Pivot to Python was created with major milestones, including replicating NCL's computational routines in Python, training and supporting transition to NCL users into Python, and moving tools to an open development model. And then finally, in September 2019, the Pivot to Python officially kicked off and the GeoCat team was officially born. So who is the GeoCat team? I'm going to give a very brief overview. We're a group of currently 6 developers and hopefully 2 interns this summer, working to create scalable data analysis and visualization tools for the Earth system science data to serve the geoscience community in the scientific Python ecosystem. We use and support an array of Python tools. I like, Mike, what you called it, the NASCAR slide. From the Python ecosystem, including Matplotlib, Cartify, XRADask, and others. We use an open development model, develop on GitHub, automate CI/CD, and other packaging things with GitHub Actions, test with PyTest, host documentations with Read the Docs, Sphinx, and in one particular case, GitHub web pages. And publish our packages on Conda-Forge and PyPy. On the right here, I have a more exhaustive, but not nearly complete list of logos of things that we incorporate and support. We're roughly structured into 3 major components, GeoCat Comp, GeoCat Examples in Viz, and Project Regine. So I'm the package leader for GeoCat Comp. So if the rest of this presentation seems a little GeoCat Comp focused, that might be my bias showing there. So GeoCat Comp is a computational component of the GeoCat project. Comp provides implementations for computational functions operating on geoscience data. And many, but not all of the functions in Comp come from original NCL implementations. GeoCat Viz and Examples make up the visual component of GeoCat. GeoCat Examples is a gallery containing plotting examples on geoscience data in the style of NCL visualizations. And GeoCat Viz provides tools to help plot data, including convenience and plotting functions that feature heavily in GeoCat Examples, and super aid with NCL style reproductions in the Python plotting Matplotlib ecosystem. And finally, Project Regine is part of a collaboration team developing UXArray, which is an XArray styled package for reading and directly operating on unstructured grid datasets following Euclid conventions. Yeah, so for the rest of the presentation, I am mainly going to be talking about a computational component, GeoCat Comp, because that is where we do the majority of our NCL to Python direct functionality translations. So this is how Development generally goes for GeoCat Comp developers. I am mainly talking about this selfishly, just to get thoughts and maybe share how we use Scrum elements in development of scientific Python. So yeah, we use some Scrum elements in the GeoCat Comp developers and the GeoCat team largely. For example, we utilize iterations, iteration planning, and retro meetings on the entire GeoCat team. However, we have customized some bits of this development to make it work well for scientific development. For instance, we add several steps to this planning phase that you can see here, the research. And we also have increased our iterations from a traditional 2-week sprint to a longer 4-week iteration planning. So when we decide to implement a function that's generally not from a user request, but just kind of like from a prioritized backlog, the first thing we do is triage an entire category of functions that exist in NCL to get kind of a full picture of the existing functionality and maybe understand some of the purpose behind the family of implementations as it exists inside of NCL as its own language. At the end of the stage, the primary developer that took on this effort will give a demo to the rest of the comp developers on their findings. From there, a developer will take on implementation research, which is more specific research into a smaller group of functions or individual functions, looking into like domain-specific research, reading papers, seeking out user input, and looking at algorithmic implementations. At the end of this process, another demo will be given to the entire group of comp developers. Once a functionality is ready for development, a more familiar agile process will largely take over, with implementation going through like several rounds of implementation and review before progressing to an approval. Once this code is approved, it is merged into our main branch, which is then released on a continuous release schedule to kind of Fortune PyPy, normally every 4 weeks or so, tied to our our iterations lasting about 4 weeks. I should also note that this process is continually improved and modified through team meetings and retro processes, and I am very interested to hear on how other scientific software development teams approach this kind of development lifecycle, if anybody has any thoughts on this. But yeah, so getting back into more NCL stuff, I want to talk about some of the unique challenges when implementing legacy code into a new language and tech stack, and generally the concept of like how close is close enough. Of course, there are ongoing conversations in the community as a whole, many different communities, and on the GeoCat team directly. And the first thing I want to point out is that on GeoCat, we do not aim for floating point accuracy from an NCL implementation to a Python implementation. There are so many factors that can affect this numerical reproducibility, such as like floating point differences, resolution of intermediate results, differences in underlying math libraries, optimization choices, differences across compilers and processors, and so many other things. For a great presentation on this specifically, I encourage you super to look at Steve Lionel's Supercomputing 13 presentation on improving numerical reproducibility in C, C++, and Fortran. I think I've been referencing this probably like since right after it was given in my undergrad days is when I first saw it, and it's an absolutely wonderful set of slides. I've pulled 2 slides from this presentation here that I find do demonstrate some of this numerical reproducibility challenges within Fortran and C, and this is even before we get to Python. So the first slide here demonstrates an example from the CAM model where a tolerance value got rounded away inside of an interior loop because of compiler evaluation. Here, AI plus B plus tall is evaluated inside of a loop, where tall is small and A and B could be relatively large. The compiler chose to evaluate this as AI plus a combination of B plus tall. And this essentially made tolerance get routinely rounded away, which is just an interesting example of this. And the second slide here demonstrates differences in a single calculation in a single language that can come up when run with different optimizations and precisions. So here is run without optimization, with optimization, advanced instructions, misaligned data, and double precision. And as you can see, each result here gets a slightly different result. And again, this is just within Fortran. I believe this is Fortran, before we even get into anything else. So moving beyond that, there are a bunch of other things that can affect these old code problems and how close is close enough. For example, decisions that we on the GeoCat team make involving reproducibility decisions include when should we update algorithms originally implemented in NCL to more modern versions if they've been developed since their original implementation? Should we make these older, outdated algorithms still available somehow within Python through like keyword arguments or other sort of ways that you can still access these older algorithms? What algorithmic changes should we make to counteract Python's speed limitations as compared to NCL's underlying faster Fortran code generally? And also, how should we address things like when we find bugs in the original NCL implementation, should we fix them in the NCL implementation? And how should we maybe document the changes in the Python implementation if we choose not to do that? These, of course, still aren't all the considerations we make when working with legacy code and creating Python implementations into an existing and vibrant Python ecosystem. We also consider questions such as what should we reproduce and take ownership of GeoCat packages? For example, NCL has a bunch of functionality that is related to NCL just being an entire package within itself, or sorry, an entire language within itself, while GeoCat is a package within a broader language of Python. For example, NCL has stuff like file IO, which GeoCat shouldn't re-implement file IO, you know. Things like linear algebra, things like SciPy that should probably handle, and when should we re-implement these, depending on how different they are in the original NCL, versus linking to existing implementations like SciPy or MetPy or other community packages. Additionally, when we find that something in NCL is missing or is a want for the scientific Python ecosystem, when should GeoCat particularly own those as opposed to other community packages such as SciPy, MetPy, or even in some cases Matplotlib owning things instead of GeoCat? And finally, a whole host of domain and usage specific considerations. In whole, I feel like the subject of reproducibility challenges in legacy code could be like an entire semester-long course. But these are just some of the considerations that GeoCat considers when implementing NCL legacy Fortran code into Python. And real quick, before I close, I want to talk about something new that the GeoCat team has been investigating and will hopefully be one of our SciParks interns this summer. So to address some of the problems I presented on the previous slide, specifically what to do when GeoCat should not like own a particular implementation, we're introducing something called GeoCat applications. GeoCat applications will be its own NCL application style page, if you're familiar with that. It is something that our users have told us repeatedly that is something they found really useful and kind of miss from using NCL in their transition to Python. But it is tailored to finding as close as equivalent of NCL functionality in the scientific Python ecosystem, whether or not GeoCat owns that functionality and develops it themselves or not. So the pages are pretty empty right now, so I've included some mock-ups instead. Again, see the SciPark Center in the summer. So imagine that you're looking for like a Python implementation of like, I don't know why you'd be looking for file IO, but linear algebra or Fourier transforms or anything like that. GeoCat likely shouldn't re-implement some of these methods that other packages have done better than we probably ever could. But we want to provide a user with specific recommendations in the existing ecosystem, which can include NCL-specific caveats, like what method keywords you might want to provide, or additional processing to achieve a very similar algorithmic and numerical effect to their old NCL workflows. Previously, we haven't had a place to give these recommendations, but now we want to build an NCL to Python style index where every NCL function can be mapped to their own reimplementations or existing solutions elsewhere in the Python ecosystem. Yeah, so hopefully watch out for that coming up. And in conclusion, thank you for letting me talk to you about the GeoCat team and our approach to writing new old code. If you have any questions, suggests, burning desires, please reach out to us. Your user input requests are an extremely important part of our development process, and we'd love to hear from you. Not to call anybody out, but especially whoever said about your NCL scripts moving to Python, please email me. And here's links to feature request forms, contact emails for my team, myself, and like my boss, if you want to email my boss, as well as a link to ESTS office hours where you can get even more direct, like one-on-one help through like appointment scheduling, which is super useful. Yeah, that's all I have. Thank you all so much.
Thank you very much for that. Yeah, really interesting presentation, both on what's going on in GeoCat and your process. Yeah, we do have time for some questions on that. And Ufuk, I don't know if you want to follow up now on that, or if you have that answered now. Up to you. And anyone, any other questions? Yeah.
So I had an unfortunately timed with your timeline conversion of all of our NCL scripts to do graphics at NOAA GSL into Python, and we made some choices. And one of them was using PyNeo as our engine for loading an X-array of grip files. And I heard you say several times, why would anybody want IO? Kind of transitioned, but GSL has been using NCL for a very long time now and have a ton of graphics that we produce at every forecast hour, every cycle of the day. And so we had a ton of information in our code, essentially in NCL, that mapped to these naming conventions of how to load all of this data in and have access. So we kept a lot of that with PyNeo as our engine to read in grip files, and I haven't found something that's kind of the equivalent of that we can use for grip files. And I'm curious, and we're stuck in the past a little bit with all of our packages. So I'm curious if anybody knows of any applications that are doing that transition of PyNeo. Or if I'm pronouncing it wrong, you can also correct me there.
I think, do you know Ed Hartnett?
I've met him, yes.
I think he's working on updating grip for reading in and out with Python.
Okay. Yeah, it's just
I'm not sure exactly, what the tool is he's doing
for sure
that with, but
So I think you're referring to WGrip 2.
yeah.
Yeah, so that gets finally rewritten. That's what I heard through the stack channels, because it's such a horrible build system that people had enough finally, and now they're going to rewrite this whole thing and making it more modern.
Yeah.
So that would hopefully help you with reading grip 2 files.
in a Python context, or getting it into an X-array. I mean, that's kind of the thing, right? Like so many of the other tools that are out there to load grip data into an X-array or similar really need you to have insight about what's in that file before you ever open it.
Yeah.
And that's tough sometimes.
Yeah, that's kind of a drawback of grip in general.
Oh yeah. Agree. But it's what we have, right?
Right.
So that's interesting.
There's one comment in the chat from Caitlin Fitzgerald. I believe X-Array uses CFGrib from ECMWF.
Yep. That one, we've been there. Not quite the thing. But this nice stacking of everything into an X-array that the NCL related codes were giving us was really a nice tool.
Go ahead, David.
Yeah. Hi, Anissa. The thing, I had this conversation with John Klein years ago, but the other thing behind the pivot to Python was talking about all these functions from NCL that you're going to move to GeoCat and everything. But there really wasn't a lot of talk about the graphics packages. And there was this PyNGL thing. And so I'm just kind of curious where your thought process is on that now. So
Yeah, so Caitlin here and Julia Kent are working on GeoCat Viz and examples. GeoCat examples is an entire gallery of NCL style replications. It's not just like plotting in Python. It's how to replicate NCL style plots in the Python ecosystem if that's what you're looking for. Though I know that maybe reproducing exact plotting routines might not be as big of a priority, though it's definitely something, especially for specific use cases that we look into, like Taylor diagrams, that maybe the Python ecosystem doesn't really have. Do you have any like specific functionality that maybe like you missed or that you wish NCL or Python has?
There is so many things. No, I've already been talking with Caitlin a lot about this.
Oh, nice.
Some of the polar plots, and in particular polar vector plots and things like that. And so it was just, anyway, I was just kind of curious about where that was sort of falling in terms of the priority list, I guess. So
I see. Yeah, I'm primarily on the computational side of the GeoCat functionality, so I don't want to like speak about their priorities.
Yeah.
Right. Great. Well, thank you again for that.
Thank you.
And I believe that, yeah, so now the next presentation will also be remote. We're now shifting gears again to some AI and machine learning pieces. And the next presentation will be a remote presentation from.
Sorry. Oh, I didn't mean to interrupt.
Yeah.
Is there a way to put the speaker
Yeah,
on
let
the
me see if I
window?
can figure that out.
All right.
Sorry. Yeah, the next person, give me just a second. I will see if I can fix something in the room so that so that we don't have a blocked piece of the screen. I don't know. Does anyone know this better than I do? That wouldn't.
Is the room pinned? Because if you if the room is pinned and you unpin it, then whoever is speaking should take. But if that's not the case,
I don't know how
then
to. Oh, wait, maybe this.
Hover over.
There. Okay, that did it, right? Yeah, I think so.
Yeah.
There is like the room
Oh,
there
now it's
instead of the speaker.
Someone who
Setting a
knows
change.
this better than I do would have to.
But that's better than it was.
Yeah.
Yeah, we can't see who's speaking. Okay. Wayne, I'm gonna probably not pronounce your last name right either, but Wayne
Chuang.
Tell us his last name, is gonna talk to us about the LEAP project, and specifically on current microphysics efforts and future plans. So looking forward to hearing that.
Thank you, Bill. Yeah, hello everyone. I'm Wayne Chuang. I'm an integration engineer at LEAP, and I'll be discussing some of my work trying to integrate machine learning using the Wormrain Taubin microphysics, and discuss some of our future plans at LEAP and machine learning within CESM. For those who may not have heard of LEAP, it is a NSF-funded science and technology center focusing on bringing machine learning into global climate models to see if we can improve some of the parameterized or computationally expensive modules. A large part of LEAP is the machine learning research in the Earth system and will be mostly what I discussed today, but I want to mention that LEAP also partners with a lot of institutions like the New York City Department of Transportation, the American Museum of Natural History, and public school teachers to increase knowledge transfer from research into the public sphere and increase engagement in climate science. And underpinning some of that work is the internal development of LEAP Pangeo, a data infrastructure that fosters cloud computing and collaboration in our research and our knowledge transfer efforts. This is a chart of many of the projects under the LEAP umbrella, split into different components of the Earth system model, and then broadly categorized into 3 different levels. The first level is where the projects are at the proof of concept stage, or at least were the middle as of the middle of last year. And these projects are, the ideas are being formed and it's getting off the ground. They're evaluating what to try and how to develop a machine learning model. Level 2 is where these models have already been developed and it works as a standalone. And then it goes into level 3, where I come in and we try to integrate some of these modules into CESM. Many of the current projects are starting out within the atmospheric realm, but there are up and coming research in a lot of the other parts of the Earth system. So before I jump into my work, I just want to acknowledge a lot of people who have worked with me on this. For a large part, DJ Gagne and Andrew Gettleman were the ones who are closely interact with and bringing ideas and helping me through this project. But I want to acknowledge too a lot of help from the Miles group at NCAR, and of course a lot of people at CESG, Cheryl, Kate, Jesse, Brian, helping me ramp up as I began this work. So the tau microphysics is a binning mechanism that replaces the original reinformation in clouds that have been modeled using auto conversion and accretion rates that were mostly from an empirical fit. So the scheme, which is placed within PUMAs, takes this bulk distribution of particle sizes and splits them into 35 bins of particles. But with this kind of discretization, it takes about 4 times longer to run as the original scheme. And so this is where we're hoping that a machine learning approach can achieve a similar result as the original binning approach, but can hopefully produce a runtime that's closer to the original bulk method. So this is a somewhat simplified view of the workflow that I've been working with, starting with data generation, which is using the original tau bin microphysics, and then testing out different architectures and selecting one that performs well. And if all goes well, the model works, and then it'd be time to try to integrate it into CAM. And then when we evaluate it in this first a single column model and then all of CAM, and then eventually evaluating with the full CESM run. Realistically, oftentimes any evaluation will come up with new bugs, will reveal some new bugs or new issues that we didn't originally see. And so oftentimes things will go back to training the model with either new variables that we hadn't considered before, or at times even going back to the data generation phase to bring out a variable that we can then train on. So, but each time that we do this iteration, we get closer and closer to hopefully the full CESM integration. So go a quick run through of some of the results. This is the offline training compared to the original physical bin microphysics. We use a fully connected neural network and look at 3 outputs that we want to predict. Barring any interesting features that you might see in the plots here, for the most part, the correlation is pretty good compared with comparing the emulated results versus the original tau microphysics results. And once we have a working model, then we look for the optimal hyperparameters. We use a optimization search algorithm developed by the Miles group. So on the left, we have the validation loss that we're hoping to maximize, and using this this search algorithm, we first look across the entire space of hyperparameters, and then once it's made about 100 runs, then it says let's focus in on this area that seems to perform the best, and then do more runs within this space to see if we can achieve anything better. And on the right side is just the full display of all the hyperparameters that we've been looking at, where they lie in terms of how the search algorithm looked, and where in orange the cluster that it dove much deeper in and tried to find the best one out of those. So once we have this model with the best hyperparameters, we want to integrate that into CAM. The way this was done was actually writing the neural network code into Fortran as an emulator function, and the results of the original training, which was done in Python, is then saved into a file, and then Fortran would read that file, load in the weights and biases, and then when you run CAM or CESM, then the results would go into this emulator and it does the calculation. So I was able to run some make some CAM runs. I did a 12-month smoke test. For the most part, for many parts, it seemed to work pretty well, but we are still concerned about the liquid water path, which is showing some over-predictions in the Southern Ocean and Southeast Asia. And so this this probably will involve going back to the model development and seeing what else we can do there to improve these predictions. But I'll switch gears now to talk about other work in the machine learning space, where we're trying to figure out ways to allow Python and Fortran to communicate with each other, because working with this hard-coded, fully connected neural network was very tough to write and maintain. It's difficult to accommodate any new or different architectures. And so one of the ways is if we can have a bridge that allows CESM to interface with a Python-based machine learning framework, this will make it much easier to try out different architectures and different schemes. Some of the things that we're looking at in terms of criteria is the ease of use by people who are unfamiliar with the CESM code, so new junior scientists, other developers and software engineers. We want to have the bridge to be easy to compile and link between Fortran and Python, not have a lot of additional or complex dependencies, and support for a lot of different machine learning architectures. Given the continuously advancing field of machine learning, we want to be able to bring in some of the latest available methods that may more accurately emulate the Earth system. Of course, there's other criteria such as execution speed that we'll eventually take a look at, but first we want to make sure that we have a bridge that will get used by the community. And there's a lot of existing bridges out there, some in greater use and adoption, some that are better supported than others. And we're hoping that we can eventually choose a few out of this list to run through. Some of these focus on bridging to Keras, some to PyTorch, and so it splits depending on which machine learning framework package we want to use. It's another decision point that we may consider. But for now, I want to highlight 4Py that enables communication between Python and Fortran through NumPy arrays, which I believe Will Chapman will talk about after this, so stay tuned. And I'll end with looking at some of the projects that are coming up and was just awarded for LEAP's year 3. There's a lot of atmospheric projects that build on the previous work from the first 2 years, such as the ice microphysics, and more work on warm rain. And the slow march of these projects towards level 3, which will eventually land on my plate. And there's more projects at level 1 that will put emphasis on data science. So there's a lot more to look forward to, and I'll end there. Thanks.
All right, thanks very much. Yeah, Jim has a question.
Wayne, nice talk. The second half of your talk, I was thinking the whole time, wow, he's given a great introduction to Will's talk. I saw that you brought that up at the end. But in the first part, you talked about going back to the training data set and retraining. It seems like the CESM2 large ensemble is a wonderful resource for machine learning algorithms. Did you make use of that, or have you found it useful?
I haven't looked much into it, so it may be something that I could research and employ.
I think in this case, you're training on this bin microphysics.
Yeah, which maybe wasn't part of that.
A lot of the strategies come from like a high resolution or high fidelity model. You do the training on that. So CSM or ensemble is probably not a good training data set in most cases. That's the outcome. After we've done all this, you'll produce a new large ensemble that is presumably better.
Thanks.
There'll be another motivation for going with ultra high resolution. That could become a training data set. I know you don't want to. Well, yeah, another argument for again.
Any other questions, Dave?
I have a question on the Fortran Python bridge. You know, Wayne, you didn't really talk about what criteria you're going to use to determine which of those potential bridges, you know, what are we going to use to help us decide which one is the best or the best couple to pursue going forward?
I think a large part is the biggest one may be how well supported it is. If it's in active development, and there are bridges out there, for instance, the Fortran Keras bridge that is no longer really supported, and so that was one of the ones that we wouldn't attempt. That's probably the first criteria, and then the second, I would say, then it comes down to how easy is it to link up, and how easy is it to test.
Yeah, I can comment on that too. I'll just say that. Never mind. Yeah. I'll say something.
Okay. Is there any other questions on? All right. Let's thank Wayne again. Now, just actually, before we transition, we have a couple minutes. I just want to read Caitlin Fitzgerald's message from the chat, especially for people in the room. She says she said feedback on IO challenges, back to the previous talk, feedback on IO challenges and or missing items from Pinio or Pingle return maintenance mode would also be very welcome. And there's a good summary of support channels in the GeoCat comp docs, which is another link that you won't see, but I have it here. If people want to see that, I can send that out to people in the room. So yeah, now I guess following on the previous talk, we'll be hearing from Will Chapman on other AI and machine learning efforts in CESM. So look forward to hearing that.
Awesome. And thanks, Wayne, for giving such a good introduction to my talk. I've titled this AI ML efforts in CSM using Python, subtitle A Lesson in Pain. Not easy, but we think we have a working solution for at least one of the bridges that Wayne talked about. And I'll acknowledge Jim a couple of times in this talk, but in large part due to Jim's efforts. I'll give you a little background on what we're trying to do. I'm a project scientist in CGD, but most of my funding is coming through the M Squared Lines project, which is titled Multi-Scale Machine Learning and Coupled Earth System Modeling. And essentially, we're trying to figure out how to bridge machine learning and our physics-based model to create these hybrid models in order to improve representation of different phenomena within our coupled model space, improve our coupled models with machine learning, essentially. And the way we're doing this is kind of tackling two dominant sources of model deficiency. So we know in our climate modeling, we have these initial conditions that are passed to some dynamic core or a physics package. And in that process, we introduce sort of two main sources of model deficiency there. And one comes through representation of the physics in these subgrid parameterizations. And the other is the fact that we're making numerical approximations for the equations of motion here. So we want to try to answer the question, how can we help address these errors with certain machine learning techniques? And that's what M2Lines is doing. So that's our website there. And there are sort of two pathways in which we're trying to attack this. One is, as sort of mentioned before, we could use a high resolution model, which we think represents the physics a little bit better, learn some sort of energy closure from that space, encode that into machine learning, and the mode that I am looking at is actually to use our data assimilation systems, or the increments coming out of the data assimilation systems, in order to inform on sort of the sum of all the structural model error within the system. We then try to learn that and do corrective machine learning as we're running forward. And the big idea is there is, so how do we use data assimilation to do this? This is a figure out of Palmer and Weisheimer, in which we're showing on the bottom there a schematic of a clearly errant model that is being affected by the data assimilation system. So essentially you have the observations in the little gray line there, and the DA system is always pulling it in one direction. And you've seen the systematic motion of the DA system, which is indicative of some systematic error within the model state. You can imagine it's like this saying, like, maybe our sea surface temperatures are too cold in the Western Pacific, and the model is constantly trying to go, hey, let's warm them up a little bit. So the idea is that although we realize bias on these long time scales, if we run a model for 30 years or so, we think that a portion of that is due to the fast physics errors. So if we can correct some of these fast physics errors, time step to time step, the accumulation of those errors will lead to a better model state. And that's the big idea here. So can we design a machine learning system that best learns this correction and we run online? And as a first proof of concept, we did a full just Fortran-based solution to this that has no machine learning involved. We just basically did a flux correction with some sort of stochastic component. We ran a data assimilation system, in this case, a very simple data assimilation system, just a nudging scheme, which is not data assimilation, I should say that very clearly. We ran a nudging scheme, a linear relaxation back to a state. We collected those increments. We then re-implemented that back into model, all in Fortran world, along with the stochastic component, and we showed that we could drastically improve the model. And here is just one figure from our recent paper that just came out in QJRMS that shows these are the improvements to precipitation seasonally in a 30-year run, based on just these reinsertion of the model errors. You can see between 15 to 20% improvements, and we showed we weren't messing with the top of the atmosphere. We're doing things that were still very healthy for the model, but we could show an improvement by integrating these things. So the idea here is these are some summaries of what we're able to do. We found that the stochastic increment helped some of the modes of variability, et cetera, et cetera. If you want to see the paper, it's linked in there. But can we replace this model with a machine learning pipeline to create some sort of state-dependent correction? So rather than having a correction that was just depending on the time of year and the hour of day, which was our previous scheme, we want to take the model state, run a machine learning model on top of it, interact with that. So to do that, we kind of have this pipeline here, in which I have my machine learning model sort of represented by this complex gray box up here. So now we're collecting these increments and we want to learn this gray box. And then we want to run the machine learning and run CSM at the same time and have them talk to each other so that they can adjust the model state, correct the tractor, et cetera, et cetera. So the first step is to just create some sort of machine learning model that can learn the increments themselves. So what I'm showing you here is called the UNet. It's a convolutional neural network that essentially abstracts information by creating high dimensional latent representations of some of these states, then reconstructs it, passes it back through, and I input the model state plus a bunch of variables, variables and all, and it outputs a reconstruction of the tendencies. And I'm doing this on a global field. So it's one model that reproduces the entire long lev of CAM. And then we are trying to learn that system. So as it turns out, we can learn the increments really, really well. This is just the R squared of those increments there. And that is a latitude height plot there showing the U and V increments. And we can see that, especially in some regions, we are able to capture a lot of the representation of these increments. So now getting to the actual software engineering part, we can do this part offline. What I just showed you is we can train that model, we can do all that and create the model offline. And then we reach the headache in which we have some really complex Python environment and then CSM, which is a really complex Fortran environment, and they need to interact with each other, which is not an easy task. So I have my skull there talking about interoperability. Nobody's happy about that step. So as Wayne mentioned, there were a bunch of bridges that are essentially out there. And I identified one that I thought showed a lot of promise, essentially because of its flexibility, and it's called 4Pi. So this is a library for Fortran Python interoperability. Still was right from their GitHub page. And essentially it allows you to pass NumPy arrays to Fortran or NumPy structures to Fortran, and then throws it back the other direction too. So as long as you can get these things to link up and talk to each other, should be everything you want. You can create your Python space, you can create your Fortran space, and you write sort of handshaking codes back and forth. And at this point, I just went to ChatGPT and I said, link CSM and 4Pi, and it all worked beautifully. That's not what happened. At this point, I emailed Jim Edwards with a simple email called compiler flag issue CSM and CAM, because I was trying to do a compiler flag. As you can see, we had 94 emails back and forth, which was a lot. But eventually we did get this all figured out, and I want to also shout out Jesse and Cheryl, who I can't really compile how many like GChat messages I sent back and forth. A lot of them just frustrated, like, this isn't working, what am I doing wrong? And they were very gracious and able to help me get everything working. So this team right here is really crucial to get this go. So what needed to happen? First, we needed to create some Python common environment that had all the necessary toolboxes. Then we had to grab 4Pi and make it discoverable by CSM. So now that is in the externals file. We then iterated about 1 million times within scene to make sure that we could get the compiler flags in the right area. And again, this is Jim. And so then we had to make it so CSM can find that conda environment and the Python scripts. Again, this is all within scene. And then we had to write these Fortran handshaking scripts. And what it comes down to now is 4Pi has these call pi routines. So now I basically throw everything into a tuple here, which is the giant model state that goes into this args file. It is then handed over to a Python routine that I've called run DA machine learning CNN run. It then returns a value here. I cast that back into a Fortran array, and then it interacts. So then I just had to write this. So I wrote this Python handshaking script, and it partied. And the final form of all these externals for a very simple working example is sort of spread across 3 GitHubs at this point, but it's being worked to. We're going to have a simple working example that will be released that won't depend on all the things that I'm currently depending on. That will go into one of the branches of CSM so people can immediately grab this and use it. Some hiccups and caveats. There were too many really to name, but now we have it all figured out. But I put this up here so if people look at this presentation in the future, they will know some of the things that we ran into. So the tuple is initially passed as an empty array. I can't explain why on the first time step. So I had to make it, so your function has to be dynamic enough so that it can handle when things are changing shape a little bit. At the moment, the Python environment must be between 3.8, 310. This is for the build only. I've found that once I've built it, I can use whatever Python environment that I want. So I make a new conda environment, and then I can interact with it. Additionally, for the build, there can't be any netcdf libraries within that Python domain because it interacts with some of the netcdf libraries in CSM. However, again, when I'm running online, I can use whatever conda environment I want, and it seems to run fine. And then there were a bunch of the import numpy, which is a useful function, causes some floating point overflow. So we had to do, every time you use this, you have to write these IEEE exceptions wrappers around it. And then there's some simple XML options that were added in order to make this thing all work. So then my little guy changes from a question mark to excited because we're working. And all you have to do is write a few Fortran subroutines, some in the init, but it's very standard if you're working within the physics packages. Very, very standard. Oh, I don't know. I don't think so. I'm sorry, Elizabeth. So we have the the angle of that. Oh, this goes up. Yeah. You're only seeing my name tag. Okay, cool. That is a bad angle. So we have some handshaking routines in Fortran, and then essentially we're passing the Python subroutine just at the end of the, essentially right after the history output, right? And now these things interact and can talk to each other. So I was able to run this. It slowed down the model by about 4 times. So to do the machine learning to the corrective state, it takes about 7 hours to run a year. And that was bad. So I wrote Jim and I said, can we move this to the GPU somehow? Can we figure that out? So now there is a new GPU, directional GPU machine definition that when you're creating your case, you define the directional GPU. And that sped it up 3 times. So I want to highlight, this is the worst case scenario for putting machine learning within CSM. We're doing full global fields. We're passing a giant array. This is not single column. It should be a pretty fast routine to call between when you're not trying to do things that are like way outside the bounds of what you should be doing. So this is like worst case scenario. But we're now running on a reasonable time frame. I think it's about a 1.5 times what run without this routine is doing, which is nice. So then the only thing you have to do on the Python side is very standard, which is load your CUDA libraries and then pass all the arrays to your CUDA devices, which if anyone's familiar with machine learning, is very really set up and available to do. So now we're able to do this and run it. So again, now we have this new error parameterization sitting within physics. And here are just my final thoughts. So we have this state-dependent error correction. I would have shown some figures about how it's correcting. But right now, if you want a really good, slow way to ruin the top of atmosphere, I have a great parameterization for you. I'm working on that, and I think it will be fine. So the results are now pending. In general, the machine learning is really finicky across different schemes, and I think we've seen that over and over again. So to be able to rapidly change the architectures and rapidly adjust the weights and use some of the more modern techniques, that's really going to help with some stability issues. And that's why I'm really excited about doing things in Python world rather than having to translate Fortran, which is a lot more rigid. So we have the machine, the GPU enabled system-wide. And I was just contacted by someone from a grad student at University of Michigan. I got this all set up in another model component for them. So we know it is pretty system-wide. It seems to work well. So Jim and team, including myself, we're going to create a simple release that can just essentially be an example that can folks can use so if they want to implement this and have rapid testing. I think it would be available. So the good thing that I think, and the reason that we shouldn't be sticking to just either Keras bridges or FTorch, is this is a solution that also offers the ability of all of Python. So if you don't want to do machine learning, but you want to do some sort of maybe control theory, so you're using some Python functionality to do something fun and then say, okay, we've triggered a condition, let's change the state in some way. This is a way to do that. You're not just locked into only using PyTorch or Keras, or it gives you some flexibility. It doesn't have to just be machine learning. The bad, we still need to test how this scales given the problem space. So I think I've done just about all that you would want to do to slow the model down, and it's not that slow. So I think it's for rapid development. Also, we have 4 GPUs on the node. I'm only using 1 currently. I need to figure out how to optimize my Python script a little bit better to parallelize that space. I think we can speed up even more. There are faster solutions out there, including this FTorch library that I'm trying to work on getting in there right now. I'm working with someone in the UK that develops it. But again, that will be a very specific solution. It'll only be PyTorch, and it'll all be written within sort of the C++ binary space. Other than that, that's all I have. Questions? I can't tell you about speed or anything like that. I've only tested 1 implementation, so if that's what you're interested about, I don't know. But I'm happy to answer anything other than that.
Thanks. Very exciting. Yeah.
You mentioned having a kind of specific environment set up when you build. Once it's built, is everything contained? Like, can you just run this out of? Do you need anything in your environment, or just standard Python to support Seam all it takes?
I can't say with confidence that everything works, but I know that I built with one environment, and then I was like, I really want to use this netcdf environment, so let's just try it. So I still was using Python 3.10, but I added Xarray and netcdf and a bunch of other stuff, and I was fine with it. So I think, universally, it's not gonna. I don't know if it's true, but yeah, I think it makes sense.
I guess my question was going the other way. Like, if you build with all the packages you need, can you run with just vanilla standard Python, or do you need some packages in for actually doing the ML?
I think what the solution should be is we'll have like a system-wide conda environment that says build with this environment, and then move over to whatever you want that's specific for your case. So yeah, just having something that is like a conda load npl-ml, that would do it for us. Yeah.
We have one question online from Gustavo. Do you want to just unmute?
Sure. Yeah, thanks, Will. That was great. If I understand correctly, you were exchanging three-dimensional arrays from Fortran to Python. That's huge.
Yeah.
Like and it was a 1.5 slowdown compared to the control. So that's pretty good. Yeah, it's like you exchange a lot of information between Python and Fortran.
Yeah, and it's not the passing that is the dominant slowdown either. It's actually my models are too big. It's the model load. It's not even the GPU inference. It is just saying load these weights into my architecture. So if I can pare down my model to be a little smaller, I think we can speed up even faster. But yeah, I think there's a lot of things that we can do in order to make this run a little quicker. But yeah, we are passing really big data arrays back and forth, and it doesn't seem to be that much slower.
I just want to mention, you brought up that NumPy caused these floating point problems. And I just wanted to mention that Fortran absolutely does not tolerate floating point exceptions, and NumPy expects them. It's kind of built in. So I thought that was really interesting.
Yeah. So we have wrappers. We know how to deal with it, which is great. Yeah.
We had the same problem with the latest version of HDF5 that is now throwing floating point exceptions when it initializes, opens a file because it tests for data type now there instead of doing the build. But that's a side note. What I wanted to say is that problem with Python libraries versus other compiled stack libraries, we've come up with a solution for that for pretty much all of the UFS and also JEDI and all this kind of stuff. So if you're interested in trying something else, talk to me afterwards during the coffee break, and we can see if that is viable for you too. So.
And I know you find your solution to create bridge between the Fortran and Python, but there is a nice library called Conduit, developed by Los Alamos National Lab to create that connection. So you may want to
Add it to the list. Yeah, absolutely.
So two questions. One is, so you and Wayne are working together, or at least communicating?
Yeah,
Wayne use this that you've built to, to get away from building everything in Fortran. The answer would be.
Oh, could he?
Could
Yeah,
he?
absolutely. Yeah.
And so then the other question is, so it's great you guys are working together, and the challenge to this makes me wonder, is there what's the value in doing testing all these different bridges, or is it going to be this much work for each bridge, or is it like once you've gotten one bridge, you've worked out a lot of the details, or where do you put your eggs, I guess?
I would hope the next time would be a lot easier. This, I mean, it took a lot of mental brain space, but it didn't take that, like, we did it in a month and a half or so. So as long as you have a dedicated person to do it, and the awesome software engineers here, and they're willing to communicate, then yeah.
And then, okay, then another sort of related follow-up is, on the M Squared Lines project, there's quite a few projects working on the MOM 6 model.
Yeah.
And I'm curious whether, what are they doing? Are they taking a similar strategy, a totally different strategy? And how is that going to affect us if we try to integrate, machine learning-based parameterizations from MOM and for scaling?
Yeah, part of the reason to use 4Pi is they're starting to do that implementation over there. MOM is a lot friendlier. They didn't run into half the problems we ran into, but now it shouldn't be an issue. So I think all the problems should be solved there, and that was part of the reason for using 4Pi is they found that they could use it over there also. So yeah.
There's one comment in the chat. Will, in the UV increments picture, large areas look good, but large areas don't. Does that matter? Do you expect improvements in the increments?
Yeah, I think it very much matters. I would love to help improve this, and the way we can get improvement is a bigger model, but then that slows down inference even more. So there's going to be some balance about what the correction is versus how big the model is, and we only have something like 4 hours too. So there will be some iteration and optimization there. Yeah. So people let you know.
Thank you again. We will have a break now for about 20 minutes and return at 2:40. And I think there's some more great food that Brian has provided us. So enjoy.
Yes.
Don't say anything crazy. Okay.
All right, we have a few last but not least talks before we adjourn for the day, and the next two will both be on Club within CAM. This next talk is from Kate Calder on the CAM Club integration workflow.
All right. I am hoping that this won't take the whole 15 minutes or whatever I'm recording. So hopefully this will get us out to the ears a little quicker. My name's Kate Calder. I'm a associate scientist here at NCAR. And yes, you can see there's a lot of letters here underneath my name. I am working on several different projects, and this is just half of my time. It's been on CAM and Club. And this is going to be a little bit of a different talk, I think, than a lot of the ones we've seen so far. I think once you've been at NCAR for long enough, you start giving these talks that are a little more philosophical and historical, which is what this one ended up being. So yeah, I think these are important questions that I wanted to raise and get feedback from people, but I'm not going to have a cool AI framework to show off. So yeah, this is just a little overview of kind of how I'm structured this talk, just the motivation and goals behind this workflow and how it's evolved over the years, and the issues that we still kind of have with integrating external collaborators code here. So this isn't meant to be an angry fire. This is a campfire, and we're all going to sit around it and listen to my story today. I'm really not here to complain, okay? Not a complaint at all. Everybody's been doing, you know, everything that we can to make this as efficient as possible so far. And I'd love to have thoughts on what we can do to make it more efficient going forward. So about my motivation, Club is the cloud layers unified by models, and I'm sure Günther will get into this in more detail. I'm hoping, because I didn't actually talk to him before this, so if he has some pretty cloud diagrams, I didn't include any. It is a large and expensive higher order turbulence closure in CAM. It does take up a significant fraction of the CAM execution time as part of the physics package. It simulates a low and a large scale convection in CAM ever since CAM 6 was released. And it is developed and still developed and maintained by Vince license groups at the University of Wisconsin-Milwaukee. So you'll see UWM a lot in here, and that's the University of Wisconsin under Vince license group out there. And they've developed this cloud parameterization with several different modeling groups over the years, including CESM as well. So their repositories and software processes out at UWM are focused on having a portable, scale-independent convective parameterization, and less on how well it specifically works with the current, most recent version of CAM, which is reasonable. That's totally the way that they should be focused. CAM is a community atmosphere model. So like CESM, it has a lot of code that comes in from different places, different external partners. And we pride ourselves on being that community source for scientific code. So my question is, you know, how going forward do we most efficiently collaborate while respecting the autonomy and independence of these external groups? And we've built a lot of processes and tools to have these sort of external repositories that are included as part of our code base, which I feel is very unique to CESM. A lot of other models and code bases out there have a single repository or single code base that they maintain and manage, where we've built a whole lot of tools to try to bring in a lot of disparate sources of code. So when doing that, what are our goals? So when we have an external collaborator with a parameterization or a model that we want to include, you know, we have a series of goals. And this is, in my mind, the hierarchy of that as we bring it into the model. We absolutely want to maintain the stability and the expected functionality of our current model. So like CAM has a very in-depth suite of tests, and we cannot bring in a new external or a new bit of code until we can pass all of those tests successfully. However, the new external code, like this also applies to, say, microphysics. If we're bringing in new machine learning microphysics, it might bring in a whole new set of functionality that isn't included in those tests yet. So we always have to sort of talk about how much of that we want to support, how much we want to work, how much of that should be maintained by NCAR versus the external collaborators. The second goal would be to include that new science and functionality in the model
So make sure that it is accessible to everybody once they're running our model. And we usually do that with comp sets and name lists and build scripts. And, you know, like Jim's been working with the machine learning stuff to make sure that there's the flags that we need it seen. There's a whole range of things that we do to support external code as it comes into the model. And then there's a third goal, which I think is a little wishy-washy, but it is definitely, I think, a goal for Club going forward, and that's maintaining pathways for scientific or engineering updates that start at NCAR to migrate back to the external collaborators as well. And this is sort of the back arrow that doesn't always get held up so well, especially when it comes to code that people are really excited about. There's a lot of research that goes into the cloud parameterizations and the microphysics parameterizations in CAM because that's an area of high uncertainty for the model. So when we have people come in who are interested in working with those, how do they get their ideas from NCAR back to the people who actually own the code? And so that it can get back into the model and the new update from those external collaborators. So here's, you know, a rehash of some of those questions again. And I put up this little t-shirt here. When I was a young software engineer, there was a website called ThinkGeek, and they had a t-shirt that I remember that said, "Go away before I replace you with a very small shell script." We could maybe the question is what you're doing could be replaced by a very short ChatGPT prompt. Is basically what it comes down to. So, you know, what tools or processes do we have that can be leveraged towards achieving those goals, to making this process of bringing in external code and bringing changes from NCAR back to our external collaborators more simple and straightforward and less error prone? And then are there tools that we can develop that would improve our current processes around that? And also, if you're thinking long-term, what are the best long-term plans and processes to ensure that these processes move forward? Because right now, I'm cool with being, you know, the person who manages Club. But things can happen. I'm not leaving, but I am riding a very scary bike race this summer. So maybe you don't know what could possibly happen in the future. And I don't want our processes, I don't think that they should depend entirely on the expertise of a single person.
Yes.
So we need to have something out there that is more useful to everybody that could pick it up if needed. And, you know, I asked myself questionally, could I be replaced with a simple shell script? What about this process could I automate to make it move smoother and faster? So I want to go into a little bit of history about how Club has been integrated into CAM, because I think that this shows how we've been pushing towards this better, improved process a lot. And Cheryl's sitting here, and this is mostly her. So you can raise your hand and yell at me if you need to. But like I said, it's originally with GFDL collaborators, and the first papers were published around 2002. And then we brought it into CAM 6 to replace 3 different other parameterizations. So it made a big change in the CAM physics when we did it. And then it turns out that the Club, you can see my thing here. Yeah, the Club SVN repos and the CAM repos are still out there. And it was funny that somebody asked about this on the text message thread this morning. I saw it as well. So you can actually go look at old versions of CESM and see the external that we created. Because originally what we would do is copy the code from the UWM repositories. They had an SVN repository, and Cheryl would copy it into an NCAR-owned SVN repository. And then she would make changes to that code that were required for it to run under CAM, and do a very good job of writing up a descriptive change log of each line of code that she had to change in order to make the Club code work with CAM and our compilers appropriately. And some of the changes even included things like tuning parameters that were requested along the way, which is something that we just don't do anymore. So I could click on this if you went to my original talk had been to click on this and sort of scroll through the change log, but I don't think I want to spend time doing that right now. You guys can look at these slides later, I'm sure, and click if you have the credentials. I was super happy my SVN credentials still worked. So when we moved CAM over to GitHub, we also moved Club into its own NCAR-owned and maintained GitHub repo. So now UWM has their GitHub repos, NCAR has a Club repo, NCAR has a CAM repo. So we still have the same process of copying the code from UWM, putting it into an NCAR-managed repository, and then pointing to that one from CAM. And this kind of had some issues. Again, we would modify that code to make it work with CAM.
It was getting to be just a few lines. There weren't any tunable parameters required anymore, but there were still changes each time we did the copy. We would do it about once a year. So with all of the development that was happening out at UWM, about once a year, there would be a huge change to club that would put a big difference in the answers in the model. And it would be a big lift for the SEs that did it. And there became sort of an issue with in-car scientists who wanted to make changes to club, thinking that they could put issues or PRs into this repository that was owned by in-car, which again wouldn't get sent back to UWM. It would be more, it would take two in-house. It wasn't getting put to the external collaborators appropriately. So what we've moved to in the last few years is to have a UWM-owned club release repo. So they actually manage this repository, and they have a really nice continuous integration process where they run nightly tests using their standalone model and then update this repository automatically with GitHub Actions. So that's fantastic. And then when we want a new tag from UWM, we work with Vince to tag the specific code that he wants to go into CAM. And then we point directly to the UWM repository from CAM. So now there's less of this question about who owns this code. It's owned by UWM. And if you have suggestions or PRs or issues that you want to raise, you go to the guys at UWM because it's their code. Yeah, so that's this last point. That means that bringing in a new club external now requires no club modifications or documentations. We don't have an in-car change log in club anymore. We just use the code that they give us. There's still issues surrounding this. And this is the PR that I have up now since January. This is only half of my job. So, and it is slow, but the testing at UWM is not the same as the in-car testing. So when we bring it over and start running it through the AuxCam test suite, often we find new issues that they were unaware of there. The development CAM that they use to test is not actually the same as the in-car CAM because of their very nice continuous integration system. They need more files in their CAM repository than we have here. So there's not an actual fork of CAM at UWM, which means you can't issue an automated PR back and forth. And the goal of this, for my goal at least, is to increase the turnaround time between the repos. So the in-car and UWM have less updating each turn. So if we could move to updating instead of once a year, once every 3 months, then there's less changes happening, less changes required, hopefully less surprises each. In practice, it's been more like twice a year so far. We're still working out the process. So it's not an easy process yet. We still have to move the code modifications to the interface and the name list over by hand because they're not actually in a fork of CAM. So I'm trying to figure that out as I next. And I don't know if they need to have a CAM fork or if they can keep using their particular CAM repository and they can find a way to automate those code changes because it's similar enough if there's some tool that I don't know about. And again, I'd love to hear from you guys. It is true that in-car scientists now go through UWM instead of in-car to update the versions of club. And I think that that's an improvement, but I'm not sure if I've heard from a lot of scientists that that's an easier way for them to work with the code or if they preferred having it here at in-car. And then, yeah, I don't know if there's a better way to automate this work. I feel like this is something that, you know, I could maybe type into ChatGPT. Here's 2 repositories. Show me the changes and make a PR. I don't know. I haven't tried that yet. But there should be something out there that could make this a little bit easier. And, you know, in general, how do we manage collaborative code standards? We've started to build a code standardization in a CAM, but the club itself is managed by this external collaborator, and so we don't do reviews of the club code itself. We just have to make sure that it maintains the functionality that we expect. And that may or may not be an issue going forward. And finally, I'm going to be working on the CCPP going forward, which means that club will be in a whole new repository in a whole new state and probably require a whole lot of changes. So we'll be managing this process even more intensely once all that starts working, which I'm really curious to see how that happens. So again, I would love to have some ideas for how to make this even smoother. I absolutely don't have the answers to all this yet. Thank you guys for listening politely through the story. And I'm hoping for feedback from the groups to see if anybody has other suggestions, because I know that this is something that's common to almost every component here. Interestingly, not land ice yet. So that's good. Yeah, absolutely. Please talk to me if you have any thoughts. Thank you very much.
Yeah, thanks for that historical context and overview there.
There we go.
Questions for Kate?
So this seems pretty similar to what happens with Mom 6, and they took a kind of different direction.
Yeah.
Where there used to be like a GFDL Mom 6 repository. Then when NCAR started to use it, somehow the solution turned out to be create a like Mom Ocean Mom 6 repository that is like the main one, and then GFDL has a fork of that, and NCAR has a fork of that.
Yeah.
And so I'm not saying that this is better. I'm just saying it's a different way of doing it.
Yeah.
But like one of the things that you point out is that like now everybody goes through the UWM repo, but it wasn't really clear. Like, is there an NCAR branch in that repo that is occasionally getting up to date with, or like everything's on a main? Or
Yeah, the way that they work at WM is that they have their own branches, but they do a lot of smaller commits daily to their main development branch. And then nightly it gets moved into the release repository. So that's what other people who want the stable version take out.
I think like one thing that comes out of the Mom 6 model is that like they're very particular about how you introduce answer changing revisions. Like basically like anytime you want to change the answer, you wrap it in a flag where the default is false, and you make people turn it on if they want to use it. So you're not like, oh, we just updated from Mom Ocean and now we're getting a different climate.
Yeah, they absolutely generally do that at UWM, but it's not always possible. And again, there's a difference between, so I was thinking also the CIS group, right? So they have a whole separate repository, and NCAR has linked their release fork as well. The whole component model is a larger project. A parameterization is a pretty small piece in theory. So, the question is how much bureaucracy do you want to require of people who are only running a small part of your model? Right? Okay. Yeah.
I was just going to ask if you could speak more to the hesitation or concerns you have about moving toward a fork instead of a separate repository completely.
So for them using a fork of CAM or for
Oh gosh. So I maybe lost a little bit. Got lost in a little bit.
Yeah,
but the piece where you were taking code and copying it over to another repository and making minor modifications.
Yeah.
Is that's still an activity?
No, we've moved beyond that. So now we're pointing to their release repo directly.
Okay.
So yeah, that was kind of just part of the history.
Oh, okay.
So yeah.
Gotcha.
It was an improvement.
Okay, sorry.
So just to clarify, are they using a release branch in their GitHub directory, or are they actually creating a separate GitHub directory that they call their release?
They have so their development code is in a private GitHub repository for intellectual property reasons. And then they have a release repository that we can point to that is a public repository for security.
Got it. Thank you.
Okay.
So that's part of it too. Yeah.
Okay. So, but the release is a fork of, or no, I guess it couldn't be a fork.
No.
Okay.
Yeah,
Has
but they
to be
do have it. It
a
automatically updates, which makes me think
Okay.
that this is something that we could leverage
Right.
as well. But I'm not exactly sure
But
how. Yeah, what I kind of want is like a GitHub action that says take everything that's happened in this repository in the last 6 months and show it to me as a patch so that I can fly it to another repository.
Yeah.
But I don't know how to do that.
Oh, that is down to a single liner in Git on the terminal, like in a terminal.
Yeah.
To be able to provide a patch for any changes that have been made.
Well, yeah.
That's not going to apply nicely when you go to apply that patch.
Yes.
If there's been any like code reorganization and that sort of thing.
Yes.
The merge process or a rebase process would probably treat you better in that, but you can do that.
Yeah.
It's just going to be painful.
Yeah.
Sorry. That's why I'm asking it on the
No,
fork.
You're right. That's a good point.
If that could be a fork and you could just update it
Yeah.
with the button on GitHub, then it might be better. And you can ignore files in the merge with certain files in your repository so that it doesn't even try to automatically do certain ones where you know that changes will be in conflict and you need some intervention.
Okay, maybe we'll talk.
Yeah.
Thanks again, Kate.
How did I do timing wise with that short?
So we're going to continue with the club theme here, and the next talk will be a remote one from Gunther.
Yeah, I know how to make a
Sorry, I'm
patch from
gonna
like a
not
single
pronounce your last name.
single command.
On club
Probably just a
GPUization
Google
and performance
question to
portability.
how to do it for a series
So
of
if we can see
Yeah.
your slides.
It's just the colon and
Yeah, can you hear me?
Yes.
Okay, great. Yeah, hi everyone. My name's Gunther Hubler, and so I've been working in collaboration with lots of people porting Club over to run on GPUs, including DOE. So hopefully nobody's mad that I'm playing both sides. So thanks to Kate for laying the groundwork for explaining what Club is and where it comes from. But all you need to know about Club for this presentation is that it's some code that does some stuff. But it is useful to know. Yeah. So, but it is useful in a broad sense to know what the input of Club is, and then we can tell from that, which calculations can be done independently and therefore parallelized. But Club was designed to operate over a single column of vertical levels, but most of the computations over these vertical levels are actually independent and can be done in parallel. And the vertical levels aren't technically independent, but the dependence is hidden by matrix solve, while the vast majority of calculations done inside Club are computations of terms that are used just to create that matrix and the right-hand side. But yeah, historically, the input to Club has just been a single one of these grid columns, but now it takes a chunk of grid columns as input, and this is nice because now we can parallelize over both dimensions here. And the first step we had to take was to push loops down as much as possible. And I won't go into too much detail about pushing the loops since it's more of a general concept and not directly related to GPUization, but it's definitely the first step to take if you don't have your loops pushed down. But the main reason pushing loops down is so important for GPUization is because you can't have complex procedures inside loops. Cores on a GPU are much simpler than CPU cores, and the only things you're allowed to have in loops really are basic operations and Fortran intrinsics. That's not a strict rule because there is a directive that makes a procedure callable in a GPU loop, but it's a kind of finicky feature and best to avoid if you can. Using subroutines and functions as normal is fine, and it helps to replace vector notation with explicit loops as you go. But that also isn't strictly necessary. It just helps keep all your GPU directives consistent when you start adding them, because then they're all just on loops and you don't have to do anything different for vector notation. And there aren't any unusual challenges during loop pushing. The output should be identical, which makes it pretty easy to detect bugs. Global variables can cause problems because loop pushing will naturally change the order of calculations. So global variables might be overwritten before they need to be used. And you can make new global variables or modify existing ones to have the right dimensions, but I recommend just taking the time to remove them entirely. The other annoyance is the occasional need to duplicate procedures and give them different dimensions. You'll have to do this if you want to call a procedure with 2-dimensional arrays and somewhere else in the code with 1-dimensional arrays, which stems from the need to not have procedures in loops, because normally you just have a scalar procedure and surround it with 1 or 2 loops. Then once you finish pushing all the loops down, you can start adding GPU directives, and it's best to do this bottom up, starting with the lowest level subroutines. After the loop pushing stage, the lowest level procedures you have should only contain computations inside loops rather than function calls or anything weird. So you'll be able to start adding directives and parallel loops right away. This would be the first step here. And the GPU contains its own memory too. It's got its own RAM on it. So you do have to worry about moving data between the CPU and GPU. And the way to do that is with these data directives, which I didn't put a specific data directive, but the idea is that you have copy in, copy outs, and creates to determine what should get copied to the GPU from the GPU and what should just be allocated on the GPU. But once everything in a procedure is running on the GPU and you verify the results, you can just start moving the data statements up through the call tree and then start parallelizing computational routines on those higher levels. And as you push the data directives up through the call tree, you'll notice that you'll be able to start removing copy outs on the lower level procedures, and only need to keep the create clauses, which tell the GPU to allocate memory. And at the end, you'll want the only data copies you have to be at the start of the routine and end of the routine. So it's ACC copy in, copy out would before calling advanced club core, everything in copy in would be copied in, and everything in copy out would be copied out. And that's just so your data can remain on the GPU throughout the code. The challenges with GPUizing the code can be a lot more complex. Finding things like bugs often requires tiny iterations and backtracking to figure out exactly where the code is breaking. Most errors aren't big deals. Something like forgetting to copy an array to the GPU before using it produces a clear error message. But if you do something like miss putting a parallel loop directive somewhere, then that loop is effectively not being run. And unless it crashes from instability, then it'll just run through and produce bad results. It's hard to figure out where that's happening from. And the best way I found to fix that is just to visually scan the code and make sure all loops have parallel directives on them. Beyond bug hunting and getting used to data directives, the biggest challenge was just verifying the results. So the output from the code run on a GPU is not going to be identical to the CPU output. There's almost always going to be floating point differences. So specifically the challenge is to be able to quickly analyze output to distinguish acceptable floating point differences from errors. And the way we handled the verifying results was to use our standalone model and modify it to run multiple columns and output that multiple column data. Now, our standalone model is basically a crude host model around the core of club, which is this advanced club core call. So rather than take the time to update the whole model to simulate multiple columns, we took this approach of duplicating a single column into many columns, tweaking the input slightly, calling the core of the club code, and then outputting all those extra fake columns to a netcdf stats file, and then returning that one true thread back to the host model. And that way we could focus all our efforts on the call to advanced club core that's used in the real host models. The standalone model we have is just for us and for testing purposes. But once we had this way of generating multiple column output, what we did was we ran the code multiple times with different compilers, different levels of optimization, different matrix solving methods, things like that. Anything that we knew would produce floating point differences without being answer changing. Then we would introduce a small error in the code and generate output from that to compare with. And you want to try this with various small errors you might actually make. Things like deleting a loop to simulate missing a directive, or erroneously breaking up a loop with the data dependence. And then after we have both incorrect output and correct output that's just bit changing, I compared various metrics based on taking the differences in field values between those two, just like a netcdf or a NCDF. That's it. And large values in metrics, like percent differences in fields or maximum absolute differences, were very telling of an error. And we were able to determine a threshold to distinguish errors from bit changes. And determining a threshold was just kind of done with trial and error, but the exact threshold depends on things like the number of fake columns we used and the number of iterations we ran with. So we had to kind of set those at the beginning and figure out which cases can we run, how many columns, how many time steps, and that kind of thing. But this method was able to get us from start to finish without ever having to update the thresholds. And it was by far the main way that I detected when I had introduced a bug. Almost all of them showed up in this way. If they didn't, it was some very obscure thing somewhere else in the code. And it's hard to overstate how much this actually helped. Like running in a host model would have taken dozens, if not hundreds, of extra hours of just compiling time and running. Another thing worth noting, but not going deep into here, is that instead of using the linear algebra package capable of running on a GPU, we just made our own instead. And the main reason for doing this was to prevent the CPU code from being reliant on any single package. So for example, one option we considered to use was Magma, which is a BLOS implementation for that's packaged with CUDA. But that would make us reliant on having NVIDIA packages and using an NVIDIA GPU. We also have to find that the custom solver we made was significantly faster than LPAC on CPUs as well. And that could be for a number of reasons, like our solvers being written specifically for the number of bands we use, rather than being capable of handling general banded matrices like LPAC is, or not needing to transform our matrix representations into the form LPAC expects. The solvers also don't use pivoting like Webpack does, which is definitely worth looking more into and making sure that we don't actually need it rather than just usually don't need it. But the question of which set of directives to use is also important. There's two options for GPUizing code. There's OpenACC and there's OpenMP. The OpenACC was designed for NVIDIA GPUs and contains some parts of directives that are specific to them, but ACC directives can be used for any GPU, just like OpenMP. It's entirely up to whether or not a compiler supports it. So we went with ACC, and at this point, I'd still have to recommend using ACC over OpenMP. The main reason for that is just that I know converting from ACC to OpenMP is doable, and there's this very helpful conversion script that does almost all of it for us. We have 2,600 lines of ACC directives in Club over like 30 files and almost 60,000 lines of code, and it can take all our ACC directives and turn them into OpenMP in a matter of seconds. Pretty cool. But I'd also have to recommend OpenACC over OpenMP for performance reasons that I'll get into in a minute. But there's no fundamental difference between the two, and many other people would recommend OpenMP because it's a more widely used API that people know better. There's no real right answer there. So now, before getting into the performance results, I thought it was worth mentioning how I gathered the numbers. I measured 100 calls to the core of Club, which is Advanced Club Core, and that contains all the GPU code, and simply use the total time to make those 100 calls. And it's important to note that because that might result in smaller average call times than we would see in a global run because we aren't dirtying the cache from call to call. I also used the fake column method within our standalone model that I had mentioned before that uses similar columns to call Club with because we don't tweak the input significantly. And that might result in unrealistically small warp divergence on GPUs, if you know what that is. But I made sure that the cost of duplicating the columns wasn't included in any of these timing measurements. Now, the timing measurements I gathered too were either from Derecho using the NVIDIA NVHPC compiler or Frontier using the Cray compiler. And the most interesting difference between those two systems is that Derecho uses an NVIDIA GPU and Frontier uses an AMD GPU. Yeah, so getting to the actual results, the focus on how performance scales with problem size is the main idea here. So in all these plots, we have increasing number of columns along the bottom, and we're either looking at raw timing results, like on the left here, or the ratio of CPU to GPU runtime. And so this first plot's on looking at Derecho, which has an AMD CPU, and NVIDIA A100 is the GPU. And on the left, we have the runtime comparison at relatively small column numbers. The CPU is in blue and the GPU in red. The crossover point here is about 50 columns, which essentially means that if we have 50 columns per call to Club, then the CPU will be faster. And if we have more than 50 columns per call, then the GPU will be faster. At 400 columns, the CPU's runtime is almost 4 times that of the GPU. And by looking at large numbers of columns, we get an asymptotic estimate of what kind of speed up we observe at high numbers of columns. And from that, it gets to about 30 times the performance of a single CPU core. And using 5,000 columns, we still see about 20 times the performance of a CPU core. And we see a similar thing on Frontier. The crossover point's a little bit, 4 times larger because it's a weird CPU. It's not really a market one. It's got extra cache and cores and a slightly higher clock speed. So it beats the one on Derecho by a bit. But even though the crossover point is much later, we still see the same sort of asymptotic speed up, with that being about 30 times faster than the single CPU core at large column numbers. At 5,000 times, it gets down to about 15 times faster. The GPU is about 15 times faster than the single CPU core. And now looking at the runtime of a single CPU core against the runtime of a whole GPU seems unfair, and yeah, you're right, it is. But trying to compare with multiple GPU cores adds lots of complexity. The first problem is that making a fair comparison, you have to use the number of cores per GPU, and other issues like the number of using all the threads available isn't optimal, and there's different ways of parallelizing on a CPU that might have different performance results. And I don't have any pretty cloud plots, but I do have this nice Christmas tree looking thing where in green we see the relatively small number. Green is small runtimes, red is larger runtimes. Down the left, we have increasing number of columns, and on the right, increasing number of threads. And so we see as we increase the number of columns, the optimal number of cores increases as well. So it's not like we can just use a single, all the 32 cores and expect the best results. But it is good to note that the best speed up observed was about 4.4 over a single core using 16 threads at 2,000 columns, whereas the GPU versus CPU there is a 12x increase. And then the cost of data transfers is also important to note, because so the cost of data transfers is the additional cost incurred by having to copy the data to and from the GPU while calling. And in general, the data transfers roughly 5x the cost of running on the GPU on derecho, but at large numbers, it still beats the CPU out easily and asymptotically achieves about a 5x in performance. Similar results on Frontier. So the cost of data transfers about 3x the cost of the GPU, and the asymptotic performance ended up being about 8x out of the single CPU core used for comparison. And so, yeah, even with the data transfers included, we still see the GPU is more performant than the best we could see with using multiple CPU cores. And that's important to note too, because currently CAM doesn't have the capability to keep all the data on the GPU throughout the run. So realistically, if we ran a GPU-enabled global model, the cost of those data transfers, each call would be included. That's likely to continue until GPUs start having a lot more memory, or we start getting unified memory architectures. The next comparison, and one of the last I wanted to make, is looking at OpenACC against OpenMP runtime. So both on derecho with the NVIDIA GPU and the NVIDIA compiler, and on Frontier using the Cray compiler and the AMD GPU, we observed that the OpenMP code was significantly slower than the OpenACC code. On derecho, the OpenMP was only about 20% slower, while on Frontier, it was more than twice as slow. And these differences weren't as pronounced at small column numbers, but the OpenACC was faster for every column number I tested, which was everything from 10 to 80,000. And by profiling the code, I was able to...
Sorry to interrupt, about 2 more minutes. Yeah.
Okay. All right. I got one more slide. We'll be good. So by profiling the code, I was able to find specific loops that were actually slower, and it was odd because they weren't consistent. This one, is much slower on derecho. It's 35 times slower when using OpenMP, but on Frontier and Cray and using OpenMP, it's not slower than OpenACC. And it's the opposite here. On Frontier and Cray, this is 165 times slower than the ACC version, but on derecho, it's not slower than the ACC version. And then the last comparison I wanted to make is just the AMD GPU versus the NVIDIA GPU. And we see the AMD GPU actually wins out a little bit, and that's not really unexpected. The MI250X is about a year newer, and the Frontier was made in part with AMD, so there might be additional optimizations under the hood I'm not aware of. And then the rest of my slides are just little tips and tricks that I can skip. So yeah, I can take some questions if anybody has them.
Okay. Yeah, thanks a lot for showing us that. A lot of lessons for GPUization in general. Great to see what's being done here. Any questions? Jim?
Yeah, a couple of questions. One of them is about unified memory and how that changes. If that technology is like nuclear fusion and is never going to show up, or if that's something that's really coming in the future, how that changes developing code for GPUs. Did you understand the question in there? So unified memory, right, makes the problem of, we can't hear Gunter. Okay.
Yeah. Huh. Oh.
We lost him?
Lost him, maybe he's joining.
I scared him off with my question already.
Can you hear me now?
Yes, there you are.
Yeah, strange. I don't know what happened. I turned my webcam on and my mic turned off. But let me open the slides back up here. The unified memory is definitely interesting. I'm sure it's coming. We already see, desktop grade systems have that. You know, the new Apple M1 chip has a unified architecture, and AMD has their own, and I believe Qualcomm's making their own. But I guess I don't have a sense of how close it is on, you know, high performance systems like on Derecho and Frontier yet. The one on Cray offers much higher bandwidth, it seems, than on Derecho. Did I say Cray? I meant on Frontier. That with AMD, where the AMD CPU and the AMD GPU are together, and we see only 3x in cost due to the data transfers. Around Derecho, we see a 5x. So I'm sure it's coming, but yeah, I guess I don't know how soon.
I would say that's the new tax system that's being installed will be the Grace Hoppers, and it has a 900 gigabyte a second between the GPU and GPU, which is more than our CPU bandwidth on a single node.
Okay.
Yeah,
it sounds very exciting.
Yeah, and then the second question is about how many columns is it practical to run climate model? You know, if you're running a climate model at 1 degree, how many columns can you put on a GPU?
Yeah, that's I guess another kind of hard to nail down question, because it depends, I guess, mainly on the number of nodes you're running on and the resolution you want to run at. So, you know, if you want to run a 3-degree simulation on a single node, you're going to have to put all of the columns on that single node, and well, you're not even going to be able to. You're going to run out of memory. But you know, if you have tens of thousands of nodes, maybe you only have a use for 50 columns per node, and then you would have to, only CPUs would make sense. But yeah, I guess it's not clear. You'd have to define the number of the resolution and the number of nodes you're running on before you can really answer that.
And I was looking at numbers while he was talking. I need to look at your numbers, Gunther, but like in any 31 degree with a PG3 physics grid is, 46,800 physics columns. So if you start doing, if you do 4 nodes, which we run on 512 cores, it's not a lot of columns per core, but if you do 4 nodes, each with 4 GPUs, 3,000 columns, which looks like it's a decent bit faster here.
Okay.
Nice. Yeah.
Okay. Yeah, that's interesting.
Great. Any other questions? Not, we'll move on to our final talk. Let's thank Gunther again. And then Gunther made a point that there's a piece of that last presentation that's a nice lead into our final presentation on testing and how you ensure that you are not introducing bugs given that you can't get bit for bit results. And so Allison Baker is going to talk more on that topic with telling us about the ensemble consistency tests for Earth system model development. So Allison, let's see. Are you going to share your screen?
Sorry, I'm trying to share my screen.
Okay, good.
It gave me some message about my settings not letting it be recorded. So let's see.
Are you on a Mac?
Yes.
Go to like settings and permissions and sharing, and then recording, and then you check the box for Chrome or whatever browser you're using.
Okay, open system. Sorry about that. Let's see. Chrome. Oh.
Yep.
And if you're having issues, you can send.
Tell it said she left the meeting.
Oh, okay.
You might
Should be better.
start Chrome when you do that setting.
Yeah. Right.
Mm-hmm.
Sorry about that.
There, she's back.
Do you have my slides there? Do you just want to show them and I'll talk?
Do we? Let me check. Do we have? Yeah. Okay. Yes, we can do that.
Yes. So sorry, I was supposed to be there in person, but I got myself a cold this weekend, so I didn't want to infect everyone.
Here. Yes.
I can just start talking. Oh,
Yeah,
there we go.
but
Thank
now-
you. Sorry to
Yeah,
cause
no,
problems.
no problem. Okay.
Slideshow, yeah.
Okay, so this is work that I've been doing for many years, mostly with Doran Hammerling and a number of other people, some of whom are sitting in the room, I think. Go ahead and go to the next slide, please. So I'm going to start with a basic overview that maybe some of you have heard before, if you've heard me talk about this, and then I'll get into some more recent work that I've done. So basically, this has already come up a few times today, even in the last talk about, how it can be hard to tell if something is correct or not. And when we think about CSM, it's really hard to get bit for bit reproducible results. You have to have all these things that don't change, and that's not usually the case. Next, please. In fact, I'm almost all the things we've been talking about today, porting to new environments, compiler change, all the optimizations everyone's doing using GPUs, all these things result in solutions that are not bit for bit identical to what it was before. So basically this came out, I don't know, 7-8 years ago, that really we have to make sure that changes that just happen during the CSM development are not negatively affecting the results. We want to make sure that it's just caused by, round off error or something and not a bug. Next slide, please. So this is a slide I've shown quite a bit. Imagine that we ran CSM, let's say on our old machine, Cheyenne, and now we upgraded to Derecho, and we try and run the exact same thing. And now the output for this model we ran is not the same. So the question we're trying to answer is, well, how do we know if it's correct? Next, please. So what we really want to know is the new output still represent the same climate? Are we still going to draw the same conclusions from the data, or did it somehow change the climate? Next, please. So how do you answer this question? Well, I mean, there's not really a definition of what climate changing means, so it's hard to say whether they're the same or not. In the past, what would have been done when we got Derecho is there would have been really long simulations run, like, maybe 400 years on each machine. And then a climate expert would look at them and basically give the thumbs up or thumbs down. And the problem with this is, it took a long time, it took a lot of computation, and it was ultimately subjective. So this is kind of our motivation. Next slide, please. So what we decide to do is ask an easier question. This is always a good strategy, right? This question is too hard. Now let me answer an easier question. So next. So the easier question is the new data statistically distinguishable from the original data? And this is something that we could actually answer. And so we use an approach that's really common for people working in climate and weather, and that is by looking at an ensemble and using an ensemble of runs to kind of get an idea of the variability in the model, and let that ensemble of runs kind of represent the accepted climate. So now, next slide, please. So now we can compare against that. So we came up with this approach we called the ensemble consistency test. And the basic way it worked was we would create a baseline ensemble for, I'll go with the Cheyenne Derecho example here. We'd have a baseline ensemble on Cheyenne, a machine we'd been using forever that we felt good about, and we would quantify the variability in this ensemble, and we have a tool for doing that. And this is something that it's okay to be a little involved in the CSM software engineers to take care of. Then the next step would be, say on Derecho or with your new compiler or whatever change, you create a few new runs. So everything is exactly the same, except now we're on a new machine. And basically, we want this process to be quite simple, and we compare the new runs to the baseline ensemble, and the tool gives you a pass or a fail. Next, please. So this kind of works because basically there's lots of different variables. I'm going to talk about CAM for now. That was the model we started with. You know, there can easily be 200, 300, 400 output variables. And just by doing these initial perturbations, these small perturbations of the temperature, a lot of spread happens. I mean, these temperature perturbations is how they created the CSM lens 1 and 2 ensembles. So those of you who are familiar with that know that they look quite different, the different ensemble members, and that actually happens really fast. This plot, which it's not important to see the numbers, but this is just 3 variables, and this is 45 time steps, and you can just see the distribution already growing. And the next slide, again, this is all the CSM variables that are output in a particular version of CAM. It's not important to see what they are. What's important is that dark red means there's only one significant digit in common, and the lighter color means more, and this is for 10 time steps. So it's just showing how quickly the output is diverging between a perturbed run and a non-perturbed run. So basically really fast. So next slide, please. So basically, when we initially started this work, we were doing year-long runs, but this is work that Dan Milroy did. He found out we could actually look after 9 time steps and notice if something had happened or not. And all we needed to look at was the mean of each field. So this was pretty cool. Next slide, please. Right, so we have all our global average variables, and we're looking after a short amount of time, and basically we're trying to see, you know, what's the statistical difference. Now, one problem is, if you've looked at the output variables, you'll know a lot of them are highly correlated. I mean, sometimes you see temperature, temperature max, temperature min, you know, there's lots of variables that are correlated. So it's difficult to be like looking at in just the variable space. So instead we use principal component analysis. Next slide, please. And the reason we use that is that by doing that, we can look at a lower dimensional space. I'm sure many of you are familiar with principal component analysis. We can also standardize the variables first, because there's a lot of different scales going on in the output variables. And the other thing that's really nice is now we can capture when the relationship between variables changes, not just the variables themselves. So instead of comparing variable values between the ensemble and the new runs, we're comparing these scores to the distribution of scores in the principal component space, and that works really well. Next slide, please. So I mentioned this already. Basically, this approach, we can look at catch when the relationship between variables is off. This is important because, you know, it could be like really sunny one day in the model, and you're like, okay, it's really sunny, but it's not outside normal. But it could also be really rainy, which you might think is okay too, but it shouldn't be really rainy and really sunny. And so you do need to capture like the relationships between. I'm gonna skip the rest of the slide. You can go to the next slide, please. So this works really well in practice. I mean, we've been using it in CSM with CAM for a number of years. It's nice because you don't need climate modeling expertise. We've caught a lot of errors this way. We've done a whole lot of testing. And yeah, so next slide, please. So what we've been doing recently is we wanted to figure out, you know, how can we apply this recipe, or how can we even come up with a recipe for applying this kind of ensemble consistency test to new models? And in particular, we've been working with Michael Duda with MPAS A, figuring out how to apply it to that. And then we also retook a look at CAM, because when we originally developed ECT, we were working with CAM 5.3, and now it's CAM 6.3. There's a lot more physics and stuff going on in the model. So we wondered, did we need to update this? Next slide, please. And this is work, excuse me, that Teo Price Brancucci has been doing. He's a grad student at CU. He was unable to talk today because he's actually in a conference in Italy, the poor guy. But hopefully he will give a talk this summer at the workshop and go into more of the gory details here. But basically the things you have to figure out for this approach are, how long the runs need to be. 9 time steps, more than that. How big does the ensemble need to be? How many principal components do we have to have? What kind of spread in the distribution are we going to look at to keep a false positive rate that we like? Next slide, please. So basically, Teo and I and Dort, but mostly Teo, worked up an approach on how to do this, how to determine all these things. And I'm not going to go into all the details on that. Next, please. But basically, just to give you an idea, CAM 5.3, we were working with about 108 variables that were output. That's after we excluded some. And there we had worked out all the parameters for CAM 5.3. And like I said, this was 6 or 7 years ago. When we went to MPAS, you can see that we found a lot different parameters were needed. And this is all about, making sure that we're running the tests long enough, that the perturbations have gone through the model long enough, that the distributions of variables have kind of normalized, and also looking at enough principal components to make sure we're having a low false positive rate. And then you can see we took a look at the newer version of CAM. Now we have almost 3 times as many variables. There's a lot more going on. We're having to look at more principal components to capture the space. And we're made the ensemble quite a bit bigger, which I know that seems huge, but these are only 7 time step runs. So it takes like less time to run them than to copy them to storage and compress them. But anyway, so this been really cool work that Teo's done. Next slide, please. And just to give you an example, this is for MPAS, some of the things that we check once we come up with the parameters on the test. There's a lot of things that, shouldn't change the climate. Like if you change the first row is compiler. If I compile with GNU instead of Intel, I hope that now I don't see a totally different climbing. So the failure rate being really small is what we want. Basically, we target 0.5% false positive rate. Changing the core counts, we don't want that to change the climate. Compiler optimizations. Now, one that does change the climate is the precision row, which I should have highlighted, but we ran the whole code in double instead of single precision, or actually the reverse. And you can see that that does make quite a bit difference. And then one problem that I'm super interested in, and this happens with CAM too, is that if we compile with or without a fuse multiply add compiler option, that does significantly affect the results. And that's something I hope Teo's going to look into more this summer. So this is just kind of a subset of the many, many tests that we do to make sure that we have things tuned properly. Next slide, please. So yeah, this is my last slide. I mean, this has been good in practice. I think it's been really useful for people in my group. I know Jen has been a big user of it for checking GPU optimizations. I think it's pretty easy to use. I've talked to Brian lately. We really don't want people relying on bit for bit, and I'd like to expand this approach to other models. We do have a module for POP, but we haven't looked at MOM yet. And yeah, anyway, it seems to be working out great for MPAS, and Michael Duda seems happy with it. The one big looming question here is that that we've worked on a little is finding the root cause of failure when you get a fail. So for example, I don't exactly know why the FMA cases fail as far as like, are there particular parts of the code that are sensitive to it or not? So we've done some work to help give more information when there fail, but there's a lot more to do. Anyway, I think that's about it. The next slide just has a bunch of papers. Like I said, we've been working on this for a number of years with different people, and hopefully Teo's paper will come out soon because he is trying to graduate in the fall. Anyway, thank you.
Thanks a lot, Allison, and yeah, thanks for both the presentation and for all the work that you and your group are doing on this very useful tool. Questions for Allison? Jim?
Yeah, Allison, you said that the CAM 6 requires a different number of, or has a different number of variables and requires a different analysis than CAM 5. But as far as I know, GN is still using the same method that we used for CAM 5. Is there going to be at some point a way to know that you should change the method and know how to change the method?
Yes, so hopefully I'm going to put out a new release within the next month or so. And I've been thinking of exactly how I should do the defaults for different models. I'll probably have some kind of JSON file or something with suggested defaults. Eventually, we do want to do an automated tool too that would basically go through the recipe that Teo's developed and kind of automatically figure out the best parameters for everything. Yeah, does that answer your question?
Yeah, I think so. Thank you.
Yeah.
We have a question online from Keith Lindsay.
Okay.
Hi, Allison. Thanks for the presentation. One of the risks of having the short runs is that there might be branches of the code that don't get executed. Is there a way of doing code coverage of the ensemble to convince yourself and to see which branches of the code have actually been exercised with this tool?
Yeah, so no, that's a really good point. I mean, actually, and I didn't talk about the ocean, the way we do consistency testing for the ocean, because it's a little bit different. I actually do look at 12 months because scales in the ocean happen more slowly than the atmosphere. But yeah, I don't have anything now that does code coverage other than kind of input from the code experts themselves. I mean, there is some scientist involvement needed to kind of look over the output variables and be like, yeah, these are ones that are going to cover what I care about. So, but yeah, I mean, I for sure put bugs in the code that I wasn't able to catch at 9 time steps. Like I changed something in in the land model in a deep soil parameter that changed absorption, and nothing happened after 9 time steps. And in that case, I ran the ensembles for longer, for a year. But that's yeah, so that's a bit of a fuzzy area, I guess I should say.
Thank you.
I was just curious if you can talk about how you might change the configurations of each of these things and how that might impact the principal component analysis or the number of variables that you might need to use. So for example, if you wanted to run a whole suite of impasse runs at different resolutions or with different physics settings, would you need different ensembles to capture the spread and the error that grows from each of those different configurations, or have you seen evidence that it makes sense to be able to use the same error growth in each of those?
So I haven't found, so the main thing I found that would affect the ensemble length is if you have the ensemble run longer, then you don't need as many ensemble members in general. For example, for CAM 5.3, when we did 9 time-step runs, we used 350. When we did year-long runs, we used 150. Of course, it's way cheaper to do 359 time-step runs than 150 one-year runs. I think that's one question you asked. The number of principal colognes you need it depends highly on the number of basically the dimensionality of the space, which is roughly indicated by the number of variables in that, CAM 6.3 has way more than CAM 5.3, but not exactly, because many of those may be correlated. Yeah, let's see. I feel like there was as far as changing like the resolution. So this test is mainly aimed at checking when you don't expect the science to change from a modification. So if you had an ensemble at a coarse resolution and you did a fine resolution run, you wouldn't want to check that against the coarse resolution ensemble, because you wouldn't expect the climate to look the same running with coarse and fine resolution. So it's really more about catching things where you don't expect the science to change. Did I answer your questions?
I think so. I think I'm hearing that you would want an ensemble for each of the various configurations that you're running.
Yeah, I mean,
Test suite.
yes, you would, except in practice with CSM, I think, like with CAM, I think they just basically test a single resolution and a single setup, because, like as Keith said, if you're exercising all the bits of the code, then it should find it. What wouldn't happen is if you have code that only runs at high resolution and you're doing your testing at low resolution, then obviously it wouldn't catch an issue in that. Does that make sense?
It does. Thank you.
Yeah.
Cheryl. So 6.3, when you say CAM 6.3, it has gone through a lot from the beginning of 6.3 to the end. So I'm curious, are you using, so currently in CAM, we have introduced in that stream CAM development, which is going to be known as CAM 7 at release time. Are you using CAM dev as opposed to just plain CAM 6?
That is a good question. I am using a really recent version of the CSM development branch.
Okay.
So CAM 6.
And when I looked up to see which CAM version it had checked out, I mean, I don't know. It looks like Jen is on the line. I was using what Jen was using recently.
Yeah, Cheryl. So it will be something very close to the up-to-date CAM developer branch.
Okay, good. And then you have to specify whether it's CAM 6 or CAM dev, and those are dramatically different. And CAM dev is the one that we're targeting with our upcoming comp sets.
I know Jan has been using CAM dev, but I can't speak to what Allison used.
I think I'm using what Jen was using.
Okay.
But I will talk to him about it, and I'll make sure that I get the notation right for what we're actually using.
Okay. And then to also let you know, we're going to have with CAM, we are introducing a number of levels that are different. And I think that should probably also have ensembles, for each of the levels. So we're going to have an FLT and an FMT. So low top, mid top, and then Wacom and Wacom X will still be. So that's just more information for you to know about.
I suspect that Wacom would be a completely different set of principal components. We've never done that, as far as I know.
And I would add that if we can get some of Teo's time in summer, we might also try this with even an aquaplanet configuration and to graduate up in terms of physics complexity, partly to track where this multiply-add comes in.
Right.
So yeah, you would need a different one for each one, but this is, we'd like a suite. Yeah.
Okay.
Yeah, no, I mean, one reason that Teo has gone through this work to kind of figure out the quote recipe is so that we're more flexible in figuring out how to, you know, modify as needed for other models and changes in models. So hopefully this has gotten a lot easier than it used to be.
Then I'll also mention that we still have a website for testing the CESM 2.1. There's an ensemble there, and if you're going to a new machine or whatever, you can just upload the 3 runs that you do on that new machine and test against our ensemble. And it's proven very, very useful.
Great. Well, let's thank Allison.
Excuse me. Okay, thank you.
And also just let's do a final thank you for all the speakers, and also bring that into it. Final thanks for all the speakers. And I also want to thank the whole admin team that helped organize this. So especially Elizabeth, Teresa, and Kaylin, and the others that contributed to this. So thank you. We do have a few final minutes if there's any pressing sort of discussion from either from today, or if people have sort of, I'm also interested if there are topics that you feel like, maybe weren't covered today, but that you feel like the working group should have more discussion on, either at the summer workshop or between now and then. So any thoughts?
And I may add to that in addition to just topics of talks, it sounds like there's already interest in doing a boot camp on IDEs, maybe a boot camp on the 4Pi type stuff of integrating. So let us know what you think would be helpful.
I personally, I was interested, like Kate talked about their process, and that was really helpful because we're all doing something that's slightly different from each other. And it's good to hear from how other groups are doing it, and part of how, it's developed for club is that because club is private, that kind of dictates how it works. But having conversations about how the development with these external groups works and all that, I think are really helpful.
Maybe that's something where we get a theme of a couple of those next time, so we hear perspectives.
Right, exactly, yeah.
Yeah, when we talk about sort of agile and fast development processes, and modernizing those processes, there's definitely a lot of places where I think we could speed things up a little bit, improve. So it'd be good to talk about it more.
Sure.
Yeah, I think Christina talked about using some Scrum in your workflow, and some of that would be really interesting to hear about. Yeah.
Great. Yeah. Thoughts? Anything else?
Let me ask everybody another question. If people aren't contributing thoughts, how do you feel about the format? I mean, in the past, we've done longer talks. This gives us a wider variety, but shorter. What's a good balance to strike here? Anybody have thoughts?
I'll say I like the length of talks today. The 10 minutes is too short.
Right.
This was very nice.
Agreed. So I just want to go get juniors and
I mean, sometimes it's good to have like a longer talk for a big topic, but it's nice to have, the 20-minute talk for something that's really focused. So
It's nice to have the multiple talks covering a single subject.
Yeah, no, that's true.
That may count like a longer.
that may be a way to do this. Like if we have a group of talks on how you interact with scientists, we have multiple smaller talks, so it's one giant team, but different
Right.
perspectives and, yeah, they don't
Yeah.
know each other, yeah.
Well, yeah, like here, we had the VS Code.
Yeah.
And there was several talks about that. I think it was the best example. There was a couple talks on club. But yeah.
They're asking if you can close the.
I think I don't know what, I don't know how to get this. But I don't know, are we,
Don't say it's better now.
Okay. All right.
Are we done?
Glad to see everyone here and hope to
86
see.
people registered for the meeting.
What-
Elizabeth just posted it. 86 people registered for the meeting. That's a
Oh,
big
yeah.
group.
Yeah.
And I was kind of monitoring it during it, and again, the IDE discussion had a lot of people come in for, and, yeah, that was really good. Yeah, so.
Good. We'll hope to see you all down the hill in a few minutes. Whoever gets there first, I think there's they're kind of setting aside a group if you just tell them you're with the software engineering working group under the sun.
Got a free beer?
Well, at least maybe have a table available for you. I don't know.